Hi, hi, Tej. It's Alexandra, and I was checking if you're here because I don't want to die from a heart attack. Okay,
All
great.
right. You hear me?
Yes, yes. I'm
Okay.
in the technical room, but I checked that I hear very well in the room.
Okay,
Yesterday we
good.
had some speakers. Uh, some of them it was okay, the sound, but some of them it wasn't, and we couldn't correct it at the time. But you are okay. You are great. The sound is
Good.
great.
Happy to hear that.
Okay, so some more minutes. We are receiving yet the participants. So
Okay.
see you.
Then we'll wait for that. I'll just tell me when I should start.
Okay. So good morning, everyone, and welcome to the second day of our International Summer School in Hydrogen and Fuel Cells. It will be a busy day and a long day, but for sure we will be compensate with a dinner in nearby near the Douro River. So let's work, and then the party will come. So first of all, I have the pleasure to receive and to welcome our first speaker, Taj de Groot. I expect to say it, have said it well. Our speaker is a professor in the field of electrochemical engineering at Eindhoven University of Technology. He will give a talk on increasing performance, flexibility, and durability of alkaline water electrolysis. Yesterday we were more dedicated to PEM electrolyzers, so today it's your turn to give us an insightful vision on how is the alkaline water electrolysis technology. So you have the floor, Taj. Okay.
Thank you. Thank you. Happy to be here. Unfortunately, not in person. I would have loved to do that, but unfortunately, could just not fit it into my agenda. So you will have to do with my online presence. I hope. Oh wait, I should also share the sound. I now realize. Can I do that? Wait. It's more complex. Yeah, then we do it without sound. Wait. Share again, and then one more. Now I hope you properly.
Yes. Okay. Okay. Great.
Yes, everything works because I don't see you. So just if there's anything, just break in.
It's okay. Start. Can start.
All right, good. So yeah, I'm happy to talk to you about increasing performance, flexibility, and durability of alkaline water electrolysis. And I always very much like to start with a picture from the past because alkaline water electrolysis is already quite old. And this is the oldest picture I have of a really operating large-scale commercial installation, which is this photo is from 1931 and was taken in Rjukan, which is the south of Norway. And yeah, this were the first 165 megawatt electrolyzer. So that's already almost 100 years ago. Just very briefly about myself, especially since I'm not there, I quickly added this slide this morning. So I am a chemical engineer, but after my PhD in electrocatalysis, I worked for a long time in industry, almost 15 years for chlor-alkali company, and that's where I built a lot of my industrial electrochemical knowledge. And only recently, I have come back as a full-time associate professor in our beautiful university, focusing on alkaline and AEM water electrolysis. Now, one thing I also first want to make clear is there is sometimes some ambiguity about who was the inventor of water electrolysis. As a Dutch person, I always want to make it clear it's a Dutch person that invented water electrolysis actually in 1789. It was Mr. Adriaan Paets van Troostwijk who first split water into hydrogen and oxygen on gold electrodes when he was playing around with electricity. He's not very famous in the Netherlands. He does have a street in The Hague, where also the NATO summit was yesterday, but he only has a Wikipedia page in English, so that is so he's not that famous. All right, so I understood that you already talked about the PEM technology yesterday, so this is just a very brief overview slide of the different technologies that are out there. So my focus here will be on the alkaline water electrolysis, the classical technology, where you make use of a 38% KOH electrolyte with a porous diaphragm. So there's no inherent conductivity in the membrane, whereas this is the case with cation and anion chains, membrane, electrolytes. So you need the 38% KOH to give you sufficient conductivity to reduce the ohmic resistance in the system. If we now briefly look at where are the different technologies in terms of progress, I think this is what feels more industrially relevant. So alkaline water is the most developed technology. You see that it has the largest stack size. In China, they make now alkaline water electrolyzers as large as 25 megawatts. And the largest operating plant is also in China, and I will briefly discuss it in the next slide, briefly show it, 260 megawatt. And the advantage of alkaline is that it's not dependent on noble and rare earth metals. At the same time, also PEM is reasonably well developed. It also has megawatt scale stacks. And in Europe, there are actually two 54 megawatt plants. And PEM is said to be compact and flexible, and you still see solid oxide and AEM at a lower development stage, making good progress. And I think the next speaker will talk about solid oxide. And I have a lot of respect for the technology because it's known to be very, very efficient. So, but generally the focus of the world at the moment is mostly on alkaline and PEM, at least for the rollout of projects. Now, also important to realize is that a water electrolysis plant is much more than only an electrolyzer cell or stack. You should always see it as part of a bigger system. The module, it contains the gas liquid separators, pumps, heat exchangers, and transformers. Oh wait, now I'm going too fast. I wanted to use my pointer. Rectifiers that make a module, as we often call it. Then we put it into a system, which also often contains a compressor, purification of the hydrogen and the oxygen, main intake transformer, and it's part of a bigger plant where you also need the civil structures. You need a hydrogen pipeline to use the hydrogen somewhere. You need a cooling system, and the parties that are involved in it. So the electrolyzer is often made by a so-called original equipment manufacturer, the electrolyzer supplier. Then we have EPC companies, engineering, procurement, and construction, that actually build the plant, and you have owner-operator companies, the Shells of this world, the Totals of this world, that operate the electrolysis plant. Why is this important to realize? Because the costs of the plant, they are partly in the stack, but it's typically less than 20% compared to the rest of the plant, which is more than 80% of the CapEx. So just to put into perspective that there is more to life than just the capital cost of the stack. Now, let me show you a brief movie on the largest water electrolysis plant in the world, which is located in China. Here you see it, and this is a brief movie.
I'm now in the Kuka city in China's Xinjiang. Around me are endless photovoltaic panels, which can convert solar energy in electricity. The electricity will be used to produce hydrogen with almost no carbon dioxide emission.
The China Petrochemical Corporation, the country's largest oil refiner, completed the construction of a 20,000 tons per year green hydrogen plant in northwest China's Xinjiang Uyghur Autonomous Region on Friday.
我们这座光伏站整体占地面积9700多亩，约相当于900多个足球场大小。总共光伏站安装了光伏组件546868块。
This is a key area of the green hydrogen project, where the water will be converted in the hydrogen and oxygen.
我们碱性电解槽制氢制氧呢，主要是通过我们当地的自来水产生的氢气跟氧气进入我们的这个气体分离装置，经过纯化之后进入我们的储罐。
These wet tanks are hydrogen storage facilities, which can hold 210,000 cubic meters hydrogen.
The hydrogen stored here will be sent to a nearby Sinopec refining company. It can replace fossil energy such as natural gas to produce hydrogen and reduce carbon dioxide emissions by 485,000 tons per year.
So I wanted to show this video because you could see some electrolyzers and also see how this plant is built up. I think European suppliers should also make these nice videos. Currently, they are not there. And another advantage of this Chinese electrolyzer technology is that it's relatively cheap compared to European competitors. For example, here there are some cost numbers for Chinese technology. For example, the plant what was just shown costs about 471 million euro, and that includes the photovoltaics and the storage and the transport that you saw. Whereas more advanced European alkaline technology costs are significantly higher. For example, the 200 megawatt plant in Rotterdam that Shell is working on, hopefully will take into operation at the beginning of next year, has an investment of about 1 billion euro. So you see here, these Chinese are doing pretty well when it comes to alkaline technology. But this is not just a PR talk. I'm an independent academic, so I can also talk about their weaknesses. And then it turns out that the plant that I just showed, that was taken into operation at the summer of 2023, after only half a year, this new news came out. So this plant has significant problems when it comes to operation. And why is that? Because, in essence, it's because traditionally alkaline water electrolyzers are not made to be flexible. And obviously, if you want to connect your plant to a solar farm, the sun does not always shine, especially not during the night. So you continuously have to ramp up and down your electrolyzer, operate at higher load, operate at lower load. And that's where this Chinese alkaline water electrolysis technology is struggling. So this is a list of KPIs, the key performance indicators I often use. And so the principle is that costs are low, footprint is reasonable, but the flexibility aspect of these electrolyzers is not great. So brings me to a couple of alkaline challenges. Because although, as said, alkaline water electrolysis technology is the most mature water electrolysis technology, it does face some challenges. And one of them, and this is the one that is faced by these Chinese electrolyzers, is gas crossover. This is what determines the minimum load. So gas crossover is the process where hydrogen leaks through the membrane, or through it can also form in another. It gets from the catalyte side, where we want to make the hydrogen. It gets to the oxygen side. So a bit of hydrogen comes into the oxygen. And that's at a high load, that's normally not a problem, because high load, because you make a lot of oxygen. However, if you bring the electrolyzer to a lower load, because there's less power available, the sun is not shining, or less shining, you produce less oxygen, and you still more or less have the same hydrogen crossover through the membrane. And in that way, you then potentially form an explosive mixture. Because the lower explosion limit is only 4%. So in practice, the consequence is that you cannot operate your electrolyzer at a very low load, because you get too much hydrogen and oxygen. And for Chinese electrolyzers, the suppliers of this plant, they said, well, they're still reasonable and flexible, or electrolyzers, apparently they promised like 30%, but in practice it was much higher. So they were less flexible. Now you can also see it in these numbers, because this shows the current density, the cell voltage as a function of the current density, and the gas purity, hydrogen and oxygen, as a function of current density for a typical Chinese electrolyzer. And basically what you want is, of course, you want to operate at a current density where you have a good efficiency, hence low cell potential, and at the same time you don't want too much hydrogen and oxygen. Now, if you look at this, you can basically say I have an operating window going up to about 3000 amps per square meter, so 0.3 amps per square centimeter, because then I reach a potential of 1.8 volt, more or less, and that's a typical efficiency we are looking for. And you also see that if you go below 1500, then you get very close, or you start hitting this 2% hydrogen and oxygen content. So here you have an operating window of about 1500 to 3000. So here you could still say, wow, this is decent. At least it's a bit below 50%, but this I think is still a bit of an idealized picture, and just shows the challenges you have here by balancing on the one hand efficiency and on the other hand crossover. So this is one of the challenges alkaline technology faces, and these are serious challenges, and that's why I show these photos, because if for some reason the hydrogen and the oxygen content becomes too high, you can get an explosion. And this is what happened in 1975 in Ilford in the United Kingdom, where actually the oxygen gas liquid separator exploded as a result of too much hydrogen in the oxygen, and yeah, you see the cooling coils hanging out of the gas liquid separator. You see the building that was damaged, and this actually one person was killed. Now, there were big mistakes were made there. For example, there was no continuous hydrogen and oxygen measurements, so some serious recommendations were made after this incident. But still, in 2019, we had another major accident now in South Korea. Actually, in this case, it was not the hydrogen and oxygen that was the problem, but it was the oxygen and hydrogen that was the problem. This is typically less of an issue, but it can also be an issue, especially if you don't monitor the quality of your hydrogen. So clearly, this is an important issue. Another challenge that alkaline technology faces is the footprint. Alkaline water electrolyzers are big things. You see here on the left an alkaline water electrolyzer. On the right, you see a PEM electrolyzer. Alkaline electrolyzer, okay, produces a bit more hydrogen, but not that much. And it weighs about 50 tons. And you see just how large a difference in size is. Now, you could still argue, hey, but this thing is still cheaper than this thing, because this thing only contains steel and nickel and some relatively cheap membrane, whereas this is full of platinum and iridium and Nafion, so all the things you basically don't want. So because it's still cheaper, but the fact that it's so big also comes at a price, because you need to bring it to the location, and when it's at its end of life, you need to take it away, you need to build a building around it. This also adds to the total plant cost. As I said, the stack is only a relatively small part of the total plant cost, so that we also need to into account. So this is a challenge for alkaline water electrolysis technology. And why is that challenge there? Because if you look at the current voltage curves, and I think most of you probably have some electrochemical background, current voltage curve is built up the equilibrium potential, kinetic overpotentials, and ohmic overpotentials. Then what we see is that the cell potential, that the line, basically the curve for the traditional alkaline systems, is much steeper than for a PEM electrolyzer. So if you want to operate it efficiently, and that's what we want, then you can only operate it at a low current density, whereas with a PEM electrolyzer, you can operate it at a much higher current density to reach more or less the same efficiency. So that is a clear challenge. So this curve, and why is the reason? So there's just a lot of ohmic resistance in traditional alkaline water electrolyzers. Also, the kinetic overpotentials are a bit higher than in PEM, but especially the ohmic resistance is much higher in an alkaline system than in a PEM system. Now, then another challenge which I only want to discuss briefly, but I do want to mention it because it's definitely one of the most difficult ones for alkaline water electrolyzers, so-called reverse currents. Normally, when you operate an electrolyzer, it's what we call a bipolar electrolyzer. So the cells are put in series, and the current goes through the cells, but there's a bit of leak current, which actually goes through what we call the manifold, the feed channels for the KOH. When you shut down the electrolyzer, what happens is that reverse current starts flowing. You get a kind of an internal discharge. It's like a battery that starts to internally discharge, and that's what you see here. I don't have time now to explain that in concept, but it is a very important phenomena, and reverse currents can quickly lead to enhanced electrode degradation. If, for example, a cathode during normal operation, it's cathodically protected, but then with the reverse current, you start to oxidize it, and in that way, you can quickly kill an electrode. Now, and then the last challenge, which is a challenge faced by all electrolyzer technologies, is just cost. If green hydrogen still has a cost problem, probably other speakers will also talk about it. That the investment cost, well, I mentioned the investment cost for the in the European, the Shell project, 1 billion euro, 200 megawatts. My own estimates are that we need about 5 terawatt of electrolyzer capacity in 2050, based on expected hydrogen demand. Maybe a bit less, but in that order of magnitude, it needs to be. Then you can make a quick calculation that corresponds to about 25 trillion euros. So that's a lot of money, and at the moment I don't think society is willing to pay that. So we need simple and robust, improved electrolyzers that are better and cheaper. So I think that's the challenge we face. Now, of course, these are the challenges we are facing. Now let's look at some of the solutions for these problems. Now, first of all, the top one is, of course, costs. How the costs are high, that's what we just said. So we need economies of scale, which is just, if you build a bigger water electrolysis plant, it will be a cheaper water electrolysis plant. It still applies. We have economies of numbers. If we can automate electrolyzer production, we can also make the process more cost effective. And a lot of companies are working on that, so that's also a very promising development. So these two things will definitely contribute, but it's not enough. If we really want to push down the cost, we also need to look at innovation. How can we further improve the technology to further bring down costs? Now just one very short video from China, where they are scaling up. So this is economies of scale kicking in for the manufacturing. These are these very large sticks. I think this is 15 megawatt or so. So a huge alkaline water electrolyzer. I'm not sure if this is the way to go, because maintaining doing the logistics for these type of stacks is quite brutal, I would say. But okay. And one thing I want to emphasize is that we have not seen much innovation in alkaline water electrolysis in the past 19 years. Actually, I should update this number now to 20. I think the photos from 2017, but not so much has changed since then, as not so much has basically changed since 1931. If you see these stacks, look at these stacks, okay, there are some subtle differences, but there is also very large similarities between 1931 and 2017. So there's and the rest of the world has not stand still. I often compare electrolyzers with the T-Ford. The T-Ford car was a very good car, very mature technology, and it would be, if we would now be driving T-Ford cars, it's the same as what we do with electrolyzers. But in practice, we don't drive T-Ford cars anymore. We are driving much more advanced cars. So we should be able to advance this technology just as we did with car technology. And that's not about some kind of completely new type of car, flying car or so. No, it's about slowly innovating. So there's no golden bullet. It's about making smart trade-offs on how to further improve the technology one step at a time, and that requires us to make trade-offs, because it's in the end what we have to think about is capital cost, energy cost, flexibility, durability. These are the key performance indicators, and these translate into physical processes that are below it. And that makes you need to make choices. For example, if you look at the thickness of the membrane, or we also call it diaphragm, then if you make a thinner membrane, it has lower resistance, less ohmic resistance. You can go to higher current densities, but at the same time, you have more crossover, more hydrogen going to the oxygen side. We'll go to that in more detail. But you have more of these trade-offs. For example, operating temperature is a very nice one. Temperature, I often see people saying we should go to higher temperature because then my electrolyzer becomes more efficient. But at the same time, when you go to higher temperature, you get more corrosion, you get more stability issues. So what's the optimum then? So we have to really look quite hard for what the optimum is. Now, so what for alkaline, as said, the current voltage curve, the curve I showed before, the black line, is not very attractive compared to PEM. And the question is, how can we basically take this line down so that we can go to a higher current density while maintaining the same efficiency? Now, you can do some very simple playing around with current voltage curve, and basically all you say is, okay, the most important thing is that I reduce my ohmic resistance, because I have a lot of ohmic resistance in my traditional system. And in my, if I would be able to divide it by a factor 5, I could be at the orange line, and I could go to much higher current density. So that's kind of what we want. Now, a factor 5, you might think, well, that's super ambitious. How do we ever do a factor 5 resistance reduction? But it's actually not that hard. Actually, we're already there with, at least from a membrane perspective, we are already there. Because in the past, we had asbestos membranes, diaphragm. And they were very thick. They had a very high resistance in this order of magnitude. Now the state of the art is a Zirfon UTP 500 made by the Belgian company Agfa. See a picture here on the left. And there you see actually it has a factor 10 lower ohmic resistance. So the resistance of the membrane is now low enough. But the question is a bit, of course, is the rest of the ohmic resistance low enough? Now, typically we say that the membrane should be dominant. So we do have a good basis here to go to higher current densities. And you also now see companies in the field going there. But as said, you pay a price for that. So because if we go to these thinner diaphragms, porous membranes, you get more crossover, because this diffusion related process, the thicker you make the membrane, the less it is. The thinner you make the membrane, the more you get. So there's clearly some work to do there. And if you get more crossover, it means you actually go to a higher minimum load. So you get the same issue as what the Chinese electrolyzers are currently facing. So that's something to think about. Now, and that's also where the research, where we in the group in Eindhoven, we work on. So we look at what solutions are there to reduce crossover while not making the membrane thicker. And one possibility is the introduction of a small gap between the cathode and the membrane. Now, why is that a good idea? Now, you see it here on the right. Why it seems to be a good idea, because here you have the gas crossover, so the hydrogen and oxygen content. If you have a zero gap, so zero gap means you push the cathode against the membrane, and also with a finite gap, so a small gap of about 500 micron, then you get the yellow point. So much lower crossover. Now, why is that? This is the positioning of this this distance matter. Now we ascribe that to so-called supersaturation. So if you push your electrode very close to the membrane, you have a high supersaturation. If you take it further away, then you don't. Now that's quite a, you can see it here in this picture. So if we have a zero gap, we have a high supersaturation at the electrode, which then directly also translates into a high supersaturation at the membrane. And that's so you always will have supersaturation at the electrode. That's just because you start making hydrogen in solution, it needs to form bubbles, which means you will have supersaturation. But if you now make a gap, then you can see, okay, I have a high supersaturation at the electrode, but it's already much lower at the membrane, and because of that, the crossover will be lower. So this is one way to reduce supersaturation. The question is a bit, what does this mean for the ohmic resistance in the system? Because now we introduce an extra gap, which leads to extra resistance. So this is something we're currently trying to find out, also with additional research in this field. And then there are the reverse. Now, on the reverse currents, just one thing I wanted to mention, also looking at the time, there are a couple of this. Reverse currents, I think, is one of the major challenges for alkaline water electrodes, because as said, they can kill electrodes and membranes. And one old solution, which was also recently kind of brought forward as a new invention again by Asaika Science, a Japanese company active in the field of chloralkali and alkaline water electrodes, and they basically proposed the idea of putting extra electrode material at the back of the electrode, which can then absorb the reverse current. I think it is a very nice idea, but this is clearly a topic that still needs much more attention, and that's what we are also working on. So this is also where I would like to come to an end. So what you should remember is that even alkaline water electrodes is not as mature as you might think. So they still face some significant challenges in terms of flexibility and costs. These things can be overcome, but we really need to work on them hard, and so there's still a significant need for research. And then at the same time, of course, we also still have this green hydrogen cost problem, which not only applies to this electrolyzer technology, but to all technologies. And maybe to emphasize, this is another photo from around 1931 of basically the same Norwegian plant in the south of Norway. I want to emphasize this was a baseload plant. So I think that's a very important difference for alkaline water electrolysis technology. In the past, these plants were all baseload. They were powered by hydropower. So here you see actually the water lines coming down from the hill. There's a lake on top of the hill. This is the power station, the hydropower station. And here what you see here is is a flat, and this flat contained the electrolyzers producing hydrogen, and then it was sent to a nearby ammonia plant. I don't have a photo of that one. So this is baseload. And baseload alkaline water electrolysis pretty controlled, but especially if you make it flexible, you have extra challenges. And this plant does not exist anymore because of natural gas was actually discovered, making it cheaper to produce hydrogen by natural gas, unfortunately, even in Norway. All right, this is where I would like to conclude with a photo from the group of students that do research in the lab. And as said, we are quite industrially focused, so that's why I took a photo of a picture with an electrolyzer, actually chloralkali electrolyzer. And I would also like to thank all the contributors that make the research possible that we do. And this is where I would like to thank you for your attention, and I would be happy to answer any questions.
So thank you, Taj, for your insightful presentation. Questions? Audience. I will start then with the first one from the online attendance. Why DAOs having a pinole or thinning in the membrane of alkaline water electrolyzer result in a voltage response for low current and OCV is less than 1 volt. It is obvious it is for gas crossover, but why do we face this low voltage response?
Sorry, can you? I missed the first part of the
Yes.
question.
Why does having a pinole or thinning in the membrane of alkaline water electrolyzer result in a voltage response for low current and OCV is less than 1 volt? Question mark. It is obvious it is for gas crossover, but why do we face this low voltage response?
Ooh, I'm not sure if I fully get what is meant here. So normally during the alkaline water electrolysis operation, we're always above 1.2, 1.3, basically always above 1.5 volts. I would say it's only when you shut down the electrolyzer that you lose that the potential starts to drop, and then basically the electrolyzer turns into a fuel cell.
Yeah.
But I'm not sure if that is what is
question.
meant by this question.
Yeah. Another one from the online participants. Great presentation, thank you. Have you also worked on the electrical modeling of the electrolyzer with respect to their integration with offshore wind farms?
We have not specifically looked at offshore wind farms. What we do have looked at is the coupling with the rectifier, especially. So normally most of our electricity grids are alternating current grids, whereas electrolyzers need direct current. So you need a rectifier to convert the direct current into alternating current, but no rectifier is perfect, is what I've learned from my electrical engineering colleagues. So you always get so-called ripples, and these ripples can influence the electrolyzer efficiency and performance. And that's something we did investigate. And in principle, generally I would say it's not a big deal, and it actually offers also some opportunities for characterizing the electrolyzer and its performance.
Yes, thanks. And here, some questions. We have room for 1 or 2 questions.
Hello, thank you for your presentation. Are you also working with AEM or just with alkaline?
We also do some AEM. Our most focus is on alkaline, but we also do AEM, yeah.
Okay, and what do you think about durability and about membrane durability for AEM?
I don't know yet, and we have to see as the numbers come out. I think, but at least I see that if 10 years ago nobody believed in AEM because everybody said the membranes can never be durable in alkaline condition. I think the field has seen a lot of progress in terms of new materials that have been developed for these anionic change membranes. So in that sense, it could go somewhere. My main concern with AEM is actually gas crossover.
Yes.
Because AEM membranes tend to be very thin, and because of that, they really struggle with keeping the hydrogen away from the oxygen. And there's not so much scientific publications yet about it. I think that will come soon, and then that will determine how successful AEM will be. I think even more than the stability.
Okay, but maybe you also could apply some strategies from alkaline, the gap, for example, in AEM maybe.
Yeah, I think actually because AEM, because you have a lower conductivity in the liquid electrolyte, the KOH, you cannot really make a gap, but you could. I think you have to look more at the strategies that are applied in PEM electrolyzers, such as recombination catalysts that work very well for PEM electrolyzers. So I guess in theory they should also be a solution for AEM or even alkaline. But I just have never seen anybody doing some proper research in this field. So I'm waiting for that.
Okay, thank you so much.
Audience, okay? They are now more active. Rui.
Thank you very much for your very precise and clear presentation. I would like to know your point of view regarding to the capillary electrolysis, promising more efficient and more conversion, better durability, and avoiding all of these problems of crossovers and gas crossovers. What do you think the capillary electrolysis can do and compete with alkaline and PEM? What is your point of view? And the other question is, do you have somebody in your group just studying like lab scale capillary electrolysis just to check how much this technology can do to the hydrogen?
No, we don't do it ourselves. I was at the Gordon Water Electrolysis Research Conference last week. And there also Gary Sweegers from Haisata was there. Normally, I'm very skeptical about all these revolutionary water electrolysis technologies. This is the one exception of a technology that I do like, and I think it's very well thought through by the Australian team of Haisata. One challenge is not the capillary. If you put the liquid on the bottom, you cannot really scale up. So you actually need to put the liquid on the top. They said they are now doing that. So I must say I'm quite impressed with the technology, and I think it's one that I'm closely followed to see if they can make it to success and scale it up and get the durability, because I think there are still some challenges. But I like the technology a lot, and maybe in the future we will also do some investigation in that field, but we haven't done it yet.
Okay, thank you.
Okay, the last one. Great presentation, thank you. Regarding alkaline electrolyzers with KOH, does hydrogen need a purification step? Would that be cost significant?
Whether it needs, that depends on how you want to use the hydrogen. So it depends on your off-taker, whether you need to purify the hydrogen. Normally you need to get the oxygen out and the water vapor for most applications, and that will add some costs
additional
but I think that applies to any electrolysis technology, that you need a bit of purification for most downstream applications. So that's not really a difference with other technologies.
It depends on the client.
It depends on the client, exactly.
Of course. So thank you very much, Taj, for your great presentation. I hope having you with us next edition. We will book it in advance.
Good.
And thank you
I would love to come.
Okay.
All right, good. It was a pleasure. Okay.
Okay. Let's moving now to the solid oxide electrolyzers. And I have the pleasure of receiving Michiel Langerman. It is for us a pleasure to have you with us. And go ahead, the stage is yours, and we will listen to you.
Check if it works. Yes, it does work. So I'm honored to be here and give a presentation on my favorite topic of research, which is solid oxide technology and the scale-up of solid oxide technology. I work at TNO, which is the Dutch research organization for applied scientific research. It is a big organization that has been established by Dutch law more than 90 years ago now. And it's a not-for-profit organization that does research for the Dutch government, but also for the Dutch and these days also the European industry. It's an independent institute with these days I think even more than 4,500 researchers and personnel. And yeah, we work on many different topics all over the country. You can see here on the right. And it is subdivided in 6 different tasks in technology. One of the biggest one is actually defense, but that was the original reason this TNO was made, to do defense research. but there is also now a lot of other things. And I myself work in the energy materials and transition domain, which has around 1,500 employees, subdivided into many different topics as well. And I work in hydrogen, of course, and at TNO, spread out over the organization, we work on basically everything related to hydrogen. So the production of hydrogen, the usage of hydrogen, the production of the green electricity needed to make green hydrogen, offshore production of hydrogen, implementation with end users, the infrastructure for hydrogen. The Netherlands is, of course, a big player in the natural gas industry. So we have a lot of pipelines and a lot of empty gas fields under the country. And a lot of research is being done to look into using that, repurposing that for hydrogen. And also, looking at policy and safety and all those things related to hydrogen, which is still something that needs a lot of attention. Now, myself, I'm located here in the beautiful dunes in the north of the Netherlands, in a nuclear research facility as well, nearby. And here we have the Faraday Lab, which is where we do all of our electrolysis research at TNO, almost all. And we work there on basically all the different technologies that are also noted in the last presentation. So we work on alkaline, we work a lot on PEM, solid oxide technology, also AEM technology now, and also, of course, the system integration and what I mentioned, offshore production of hydrogen with electrolyzers as well. And we have two labs, one for manufacturing of solid oxide cells, where we work a lot on these scale-up issues. And we work from very small cells, from a button cell up to what are the largest cells in the world at the moment of high performance, up to 30 by 30 centimeters. And we do have a lot of different technologies to make these cells. And we have also the facilities to test these cells. Mostly we started up to test our own cells and the products we make, but we also work with a lot of companies that make these systems to test their products. All right, that was just a short introduction on what we do at TNO. And I will also give a short presentation on what is SOE. I will not go too much into detail because I can talk hours on that. It's quite a complex technology, I would say. I will give a short history. And the previous speaker, and as a Dutchman, I will be very ashamed that I didn't put the Dutch inventor of fuel cells on this presentation. So I'll have to correct that later. For solid oxide electrolysis, it's actually nice. Nernst, basically sort of the founder of electrochemistry, discovered already one of the main materials of solid oxide electrolyzers and fuel cells in 1899. He found out about the ionic conductivity of Itchian stabilized zirconia, and they used in fuel cells and electrolyzers. So that's already very old. All the other technologies were also, in the next 50 years developed. But actually, solid oxide was only really, starting to take form in the 1970s with the Westinghouse tubular SOFC reactors. And not much work on it was done, like a little bit with alkaline because of other technologies that were more interesting. PEM fuel cells, of course, became very popular and also were implemented in mobility. Of course, the Toyota Mirage, very famous. They made a new one a few years ago after the hydrogen topic became popular again. And for electrolyzers, it is a bit similar. For solid oxide, it also became in the 70s. where there was by General Electric and the National Laboratory in Brookhaven, and here they made the first solid oxide electrolyzer. One interesting thing is that only a few years ago there was a solid oxide electrolyzer on Mars in the rover Perseverance to create oxygen from the atmosphere there, from the CO2. Well, the importance of hydrogen, of course, I don't really have to explain here, I hope. Water electrolysis it plays sort of a singular role here, as in it is one key figure. The use of hydrogen, of course, has a lot more applications via fuel cells in different ways. Reversible operation is also possible. I will actually focus mostly on water electrolysis because that is also the activities that we do at TNO. We have a long history in solid oxide and other types of fuel cells in the company. But since 2012, those activities have stopped, and we focus now mostly on electrolysis. Now, briefly again, an overview of the different types of fuel cells and electrolyzers. Solid oxide works quite different than the other one. Well, first of all, of course, it's a very high temperature technology, ranging, well, here it says 600 to 900, depending on the type of solid oxide, it's 400 to 1,000 degrees. And it works with ceramics, which are conductive to oxygen anions. So the electrolyte is a solid ceramic that lets the oxygen anions through. And this is enabled by this high operating temperature, which allows the ionic conductivity to take place. One of the downsides for traditional SOE compared to, for example, PEM, is that it doesn't provide hydrogen as a separate gas. It's always in large amounts of water, so there's a purification step or a separation step needed there. For SOFC, of course, it's the other way around. And just to go into a little bit more detail in what a cell looks like, or the main structure of a cell, I will go even more detail later about really what the materials are. But like I said, it has a solid electrolyte, which can be very thin, up to a few microns, up to hundreds of microns, depending on the cell type. And it has two porous layers, a cathode and an anode, that take care of either the water splitting reaction or the oxygen recombination reaction, or in the fuel cell mode, the oxygen splitting and the water synthesis. But there are different types of solid oxide electrolyzers or solid oxide cells. And I've listed them here. So there's four main types. And these three on the right all fall into a similar technology category. It's just a different architecture of the technology. So you have metal supported cells where actually all layers are deposited on a metal sheet. You have an electrode supported cells that that's the steam/hydrogen electrode that is forming the support for the entire cell. And you have electrolyte supported cells where the electrolyte can be 100 micron thick, and this is a very strong material, so it can maintain the entire integrity of the cell. And then you have another technology, which is proton conducting electrolysis or fuel cells, which actually operate more similar to what you know from PEM technology, where the hydrogen is produced separately from everything else, and you can internally pressurize this hydrogen electrochemically as well. So it is a very interesting technology. It is very low TRL. It is mostly at universities that this is now being investigated very strongly. Some companies are dabbling with it, but it's still very low TRL. It does offer a lot of potential applications, though. And one of those benefits of SOE technology is that it is not only making hydrogen. So because it operates at this high temperature, it is able to do a lot more than just hydrogen production or hydrogen utilization. It can, for electrolyzers, you can do the steam electrolysis, of course. You can do co-electrolysis, where you produce hydrogen and CO at the same time, and by matching the inlet conditions, matching the current that you use, you can exactly get the mix you want in hydrogen and CO at the outlet for industrial application. And this is, well, a near 100% Faraday efficient process, so not like low temperature CO2 electrolysis or CO2 utilization electrolysis. And of course, it can also do the CO2 electrolysis directly to CO. So this is also a very interesting reaction. What I mentioned about proton conducting high temperature or intermediate temperature electrolysis is that it can do a lot more, potentially. So it can do, of course, the hydrogen production, and it can internally pressurize this because it's a separate compartment, so that's it's very nice. It can also do co-conversion. It can do hydrogen production coupled with ammonia production by introducing catalysts to this ceramic assembly. It can do natural gas upgrading. It can do a lot of different chemical reactions as well, because it can operate at lower temperatures, up to 400 degrees. So it has a lot of promise, but it is still a low TRL technology. So I won't focus on it anymore, but just to get you excited about the world of high temperature electrolysis. So what are some of the things that are being worked on? Well, one of them is, of course, the development of SOE is still at a lower stage than the other electrolysis technology except AEM. And there are some targets that need to be reached still. So lifetime needs to be improved, current densities need to be increased, and especially cost need to be reduced. Although stack costs, like mentioned in the previous presentation, are generally only 20% of the cost of an entire plant. So actually a lot more cost reduction is needed in the balance of plant of a electrolysis plant than in the stack itself, because it doesn't contribute as much. And the technology scale up. I think at the moment the largest SOE unit is a 2.6 megawatt plant. You can't even call it a plant. It is basically a large container. So that is, yeah, the market needs to start working with it. It does have a lot of applications, because one of the nice things is that there is heat integration and feedstock integration possible with the chemical downstream industries by using waste heat from these industries, using some of the same purification steps, and also some of the steam that is sometimes produced in these systems. And overall, the energy efficiency is just way better for solid oxide technology than for the other technologies. And that has to do with this high operating temperature, because a lot of energy for the reaction is supplied by these by the thermal energy. So the electrical demand is much lower, which is of course very important, especially in Europe, where electricity prices are very high, to have as least amount of impact from the electricity demand. So you can see that here, the solid part of the bar is what you need in electricity if you can supply heat from the industry to make steam. If you can't do that and you need to generate steam yourself for the electrolysis, you come with this dotted line extra, still lower than the other technologies, but it does, you see the impact of getting free steam for this technology. One of the reasons also that, in more practical terms on current density voltage curves, on why the electricity demand is lower is because just the resistance is lower. And you operate, ideally, always the SOE electrolyzer at 1.3 volts, because this is the thermoneutral operating point of the solid oxide electrolyzer, which means that the reaction can sustain itself thermally. It generates enough heat to offset the endothermic reaction, thereby not requiring much more input heat on the system level once you have the system going. by using smart use of heat exchangers and stuff like that. One of the other benefits is that the same electrolyzer, exactly the same unit, can be used in reversible mode. So you can operate it as an electrolyzer during day, and if you need to make some extra hydrogen during the day, you can, for example, use this hydrogen at night to generate electricity by just returning the reaction the other way around. So there is also a research field in looking into how to use it as a sort of grid balancing technology. And of course, what I mentioned in the previous slides, multiple feedstocks and products are possible, which makes it very interesting for many different types of industries. I didn't want to entirely skip the fuel cell applications of it. I think yesterday there was also a talk for shipping with solid oxide. Because there are some interesting use cases. One of the oldest one is actually a sort of combined heat power systems. So in fuel cell mode, as solid oxide generates a lot of heat, and it would be useless or a waste to let it go and not do anything with it. So often they are combined with steam turbines to generate additional electricity. And you can reach up beyond 90%, sometimes close to 100% electrical or efficiency, system efficiency by doing that. So it has been deployed, let's say, in especially I think in Asia, Korea, Japan, in sort of neighborhood electricity generators. So that's a nice application. Airbus, I think 2 years ago, announced they want to make a megawatt-sized, very large Airbus plane and certify it by 2035. I'm not sure if that's still on the planning, but that was a very nice announcement back then. It has also a lot of potential for some mobility applications because it is quite a small and compact system. And now I'll go to the meat of the presentation, the upscaling challenge. So I will first go a little bit more detail in what is behind all of this. What is actually in a solid oxide? What is a solid oxide cell? So a solid oxide cell is a multi-layer assembly of different ceramic metallic elements made by various different deposition techniques in series, sometimes also laminated together. But things like tape casting, screen printing, slot die deposition, a PVD deposition that's also now getting more and more interesting because of the very thin layers you can get. And it requires multiple sintering steps at very high temperature because these are, in the end, ceramics that need to be processed. And one of the biggest challenges is if you want to develop new material, the biggest challenge is you need to select your material that it has the same sintering shrinkage and expansion coefficients. Because during operation, you operate at 800 degrees. After you've sintered it, if you have different sintering or thermal expansion coefficients, your layers might just get loose from each other or cracks may form because they expand at different rates. And the technology has a very big range of different shapes and configurations that are possible. There is not, it has not been down selected yet to some sort of ideal application or shape or form. So what I show here is an electrode supported solid oxide cell. This is also what we mostly work with at TNO, and also I think most suppliers actually work with this type of architecture. But you can see that it's, counted correctly, no, this has about 7 different layers in it. And this is what the SAM picture of it looks like. This totally is around 0.5 millimeter in thickness, so 500 microns. And here you have a zoom on sort of this part of the system, the active part of the electrolyzer component. with the very dense electrolyte in the middle, which is taking care of the oxygen anion conductivity. Like I said, there is many different configurations. So you have tubular cells, which was actually one of the first designed things, as the oldest sort of application. You have the few electrode supported, which I showed in the previous slide. You have the electrolyte supported, where you have a thick electrolyte, which also means you have to operate them at very high temperature, because you still need to get this ionic conductivity going. So you need to operate those more like 900,000 degrees. And you have the metal supported ones. This is interesting because it sort of integrates the stack materials with the cell, thereby simplifying in theory the stack manufacturing of a metal supported cell. But it comes with its own challenges. So the reason mostly working with planar cells these days is because, while it has some benefits, you can pressurize your hydrogen much easier, or pressurize your system much easier. Sealing a tubular cell is much easier, because you can actually just extend it out of the insulated hot box or oven and just in the cold zone seal it, which is way easier. It has some downsides. It's at low current density because of the long current path, so it is a high resistance, because, for example, the current generated at the bottom here has to go all the way to the current collector, all the way to the material, while on a planar cell that's has a much higher surface area to do that. And the manufacturing is much more complex. I said it takes many different layers, but that's even harder to do if you have a tubular design than if you have just flat layers on top of each other. So that's why planar cells are sort of the way to go, except for some specific applications. They can reach much higher current densities. There is complexity in the stack and sealing, but there is a much easier manufacturing. So material-wise, it is a bit interesting, because if you look in the OpenNE review on solid oxide materials, you will see an infinite amount of materials almost. Especially in academia, they are very good, of course, at making as many new novel materials as possible. But I have listed here some of the more common ones that are applied and have been proven sort of on a, well, I wouldn't say industrial scale, but by companies implementing them and in upscaling, especially outside of bottom cells to very high surface area cells, and also with reasonable degradation that looks at thousands of hours instead of 100 hours in a lab, or 10 hours. But for all of these layers, there is many different options. So the air electrode of oxygen electrode usually uses perovskite materials, lanthanum strontium based ones with different additives, so cobalt, iron, chromium, manganese. One of the most performant one at sort of intermediate temperatures at 750 degrees is LSCF, which is lanthanum strontium cobalt ferrite. But you also have different options without cobalt, which is actually a big topic of research, because cobalt is a critical raw material. So you want to eliminate that perhaps. For the electrolyte layer, or for the barrier layer, to prevent the fusion between the electrolyte and these oxygen electrodes, there's only one option basically. This is a gadolinium doped Syria layer, which works very well. And for the YSZ, the options, or the electrolyte, the options are also limited. There is, the main one is YSZ, yttrium stabilized zirconia, and some people use scandium stabilized zirconia. It has some benefits, but also has a different operating window. And for the fuel electrode, nickel YSZ or nickel GDC are basically the two main ones, but there are also some nickel-free alternatives, but those are more on the lower TRL level. But may be very interesting for next generation solid oxide cells. So when we talk about scale, no, I think in the last presentation this was already touched upon. And here you see a Sunfire stack, German company, for alkaline. This one single stack is 3.2 megawatts power. If we compare that to solid oxide state-of-the-art that you can get from a company, let's say, the surface area difference is enormous. I think 200 square centimeters versus 5 square meters. That is 0.02 square meters for the solid oxide cells. The stack powers are much smaller, maybe 20 kilowatts maximum you can get now, although that's active development, versus this thing, of course, multiple megawatts in one stack. I think it was even in the last presentation, the Chinese ones, which are like more than 10 megawatts. And the limited cells per stack. And that is something that is hard to overcome, because these are all, like I said, these cells are solid ceramics. Stacking solid ceramics interspersed with metal plates to make a stack can be quite critical, because unlike sort of membranes, polymer membranes, they can't be deformed so easily. So you can't just go to a 500 cell stack, because you may not be able to structurally, mechanically support that very well. They may all crack, or they may start to form a sort of Tower of Pisa by not having exactly the same thicknesses. So this requires sort of a different approach to system design. It is a much more modular approach. So there is multiple stacks per hotbox, multiple hotboxes per module, and a module would then be comparable to this. And many modules per electrolyzer plant. So that would be similar, but I will show some examples from that later, what you can think of for that. And from an increase in stack power, there is the increase in current density, which is very, of course, very important. At the moment, commercial stacks, 0.5 amp per square centimeter, 0.8 amps per square centimeter. In theory and in practice, it can go much higher, but it is a play between degradation and performance. And of course, the increase of the solid oxide cell surface area, which is something we are very, we have worked very hard on ourselves, and also companies are now working on that. Just to give you an idea of the actual progression going on now in a sort of timeline over the last few years, and what we are looking forward to is that over the last, well, what is this now, 3 decades? We went from 10 square centimeter to 100 square centimeter and half an amp per square centimeter to 200 square centimeter cells, which is sort of the now what you can get commercially at these operating conditions. These are not necessarily linked together, the size and the current density. It's just that these were parallel development tracks. The next generation of most suppliers is going to be around the 300 to 400 square centimeter system. If the newly announced stacks of several companies, they will be in this size range. So that's already a doubling, or for some companies, a 4 times increase. And going above 1.1 amp per square centimeter. So, and with the ultimate target by 2030 to go to 1.5 amp per square centimeter, and maybe go to even higher surface area cells, which would be very nice. So we have worked on this for now, I think, 3 years. We decided, okay, we need to demonstrate this, that it is feasible. There had been a publication, I think around the same time that we started this, from a Chinese group, which showed also 30 by 30 centimeter cell, the 900 square centimeter. But I think they had a milliamp per square centimeter performance on them. And we produced already very high performance solid oxide cells at TNO as a research vehicle. But also we have several spin-offs in the past on our technology that form the basis for some of the commercial suppliers, actually. We decided, well, we can just scale up our 10 by 10 cells 9-fold to 30 by 30, which is what we did very quickly, actually. And we managed to showcase that it is feasible. But there were a lot of challenges in that. We had a very high porosity cell, which is good in the sport, which is good for gas diffusion. But we also wanted to reduce the thickness of the cell. So this is what we sort of did. We had a 500 micron cell with high performance. We went thinner. We were able to show even higher performance. And then we decided, oh, we want to go another step to hit this 33%. Well, here it started to go wrong. This is what we saw, well, maybe 80% of the time for our samples at this point. So we went back to the drawing board because they were so brittle that during handling, just by lifting it up, moving it to the next stage, it would just shatter by putting it down too hard or just lifting it up. So we decided to keep the same thickness but reduce the porosity, which of course impacted the gas diffusion, which is a very important resistance in an SOE cell, but helped the mechanical robustness significantly. So we lost a bit of performance because of less gas diffusion, but we gained a lot in mechanical strength. So now we don't have 100% yield because we also do small batch manufacturing, so it's hard to get statistics. But let's say in a series of 7 cells, we only lose 1 by accident. That's an inversion of the yield, let's say. You can see here the mechanical strength increase, which looks small, maybe, what is it, 40%. But in handling, that is enough to get very strong cells. Yeah, so we were able to get these very big cells, and you see them here sort of in physical form. And we also test them ourselves. We may build a specific test platform for that, 3.5 kilowatts to test these single cells. We can also do a stack with it if we want. Just to demonstrate to sort of the industry that it is a way forward to go like this. So at the same time, we looked at, what does it mean for plant scale up to get to these hundreds of megawatts, 1 gigawatt electrolyzers with SOE technology? There's no examples, so we had to look for it ourselves. We did this with another institute in the Netherlands, the ISPT Institute, and 3 different commercial partners: BP, OCI, who works with ammonia, and Air Liquide, well known, of course, works with all kinds of gases. And the thing was to look at 3 business cases and make a roadmap scale to go from a cell to a 100 megawatt or 1 gigawatt size factory. So there were 3 different use cases, 4 different use cases actually, ranging from 20 megawatts for just CO production to 900 megawatts for syngas production. And we started looking first at what you can already just do by scaling up the cells. If you go from the standards of 120, 200 to 400, you can already increase your stack power from the maximum 20, what you have now, which is roughly around 40, 60 cells, 100 cells of this size, to, already for 120 cells, which is quite feasible to do, already almost 100 kilowatts per stack, which is of course much less than an alkaline stack, but you will never reach that power with SOE. And if you then go take our own size cell, 800 square centimeter active area, you can also reach this 100 by using half of the cells, or you can make a 120 cell stack and almost have 200 kilowatts. Now, I mentioned this modularity. So how does it look? Like in SOE, you have a hot box, which is the very well insulated box with all the stack or several stacks and some hot balance of plant items, so such as heat exchangers and electric heaters, which is one part. This is very well insulated, very low heat loss required. Of course, you operate at very high temperature. And these are then combined into a building block. I use the word module here. Where the purification or some compression and power electronics are. And this you can basically keep repeating. And then on a plant level, plants, not plants, you have the larger purification, you have the storage, you have the electrical, the current transformers, you have the steam supply, generators, and all kinds of other things, which is plant-wide. And from discussions with suppliers, they found that sort of for a hot box, the 0.5 to 1.5 megawatt was an ideal size when you also come to power electronics and stuff to feed this, and also all the hot box balance of plant stuff. But there's no consensus on configuration, and that depends a lot on your maintenance strategy and the application of this. So you can have different ways to do this, right? So you can actually do it with smaller hot boxes, separate. If one breaks down, you can take it out, replace it very easily. That's much harder for the 16 stacks in one hot box. You can also separate the hot balance of plant in its own hot box, so if that fails, you can exchange it. So there's different strategies for modularity. But with this, using this type of way of looking at it, you can already get an 18 megawatt module that has the size of 3 to 6 20-feet containers. And that is a very small footprint. Actually, when it comes to footprint, and I don't have time to discuss it much in detail, SOE is considered to have the potential to have the smallest footprint of all the electrolyzer technologies, especially related to the balance of plant. We use a lot less water because it's all steam. So it's all the gas, and we use almost like 90% of the steam that you feed to the system is used, instead of for alkaline and other systems where there's infinite amount of water and you just utilize a small amount of it. So there are a lot of companies in Europe especially working on this on different scales, but all of them are scaling up. TUPSO is a big player, Elcogen, and Sunfire, of course. Sunfire has the largest deployed capacity, but these other companies are working on very large production facilities to be able to produce a lot of stacks per year. And TUPSO, for example, is now looking with American company to deploy a 500 megawatt solid oxide system for ammonia production. And what this looks like, well, they're all building their big factories now to do this. This is, I think, a 10 megawatt, the next generation from Sunwire, a 10 megawatt module. And this is actually designed by TUPSO, and where other electrolyzers, especially alkaline, usually you can only do it horizontally. They don't want you stacking up. They actually looked into just stacking up these hot boxes on top of each other to save even more space. So there's a lot of activity going on, and I think the next few years will prove critical to showcase that you can actually get these larger systems in the market. And with that, I would like to thank you for your attention. If you have any questions.
Thank you very much. We have time before our coffee break, 2 or 3 questions.
Hello, good morning. Thank you for your presentation. So I have a question. I'm not very familiar with solid oxides. So since we are here talking about green hydrogen and integration with renewable energy, how do they combine with the intermittency of the renewable energy? Do they respond well? Does the response time is adequate to operate them with basically renewable energy?
That has multiple answers. Because it is not really known yet in detail. There is different studies being done on lab scale with like one stack, looking into intermittency. A lot of European projects working on this, consortia. There's mixed outcomes of that. But one essential part is, if you want to ramp down an SOE system, you have to keep it hot. If you start cooling it down, it's game over. That's actually not entirely true, but likely in such a big system, if you have multiple module stacks, then it is indeed a big problem. We have shown in the lab that you can actually just cool it down and start it back up and you get the same performance, but that is on a single cell level, not on the stack level. But that only takes, I think, 5% of the total energy of an electrolyzer to keep it running. So you could do that if you take that cost into account, you could do that in a sense. Because if you keep it hot, change the gas composition that you feed to it, have it looped, recycled, then you should be able to do it. And there's also some interesting work being done in Denmark by a startup company that works on DC-AC operation by very rapidly changing the frequency. The total sort of power is still roughly what your operating power should be, but by doing this high frequency operation, you can reduce the degradation, and you can also ramp this down more easily. So there are ways to, but it's not really known yet, let's say. But don't cool it down. Keep it hot.
So if you maintain the temperature with an external system, you can operate the different
and there's
power
always
levels.
electrical heatings, because when you start up the system, you also need the electrical heaters to heat up your steam to the operating conditions before you start the operation.
Okay, thank you.
Okay, thank you very much for your presentation. Regarding to the durability, durability is a huge issue in high temperature electrolyzers. The efficiency, it's a very great advantage, right? But in terms of durability, what is your experience regarding to durability? How many real-time hours can you operate your electrolyzers in ideal conditions, right? With the right power, and how much they really last?
So I know from some suppliers, like Sunfire, they have demonstrated on a stack or system level, the systems they have, that they actually have, I think, below 0.1% degradation per 1,000 hours, which is actually in the range there where you want it to be. On a lab scale, we have also demonstrated some below 0.4% degradation, and those are real operating conditions. So not easy mode, they're quite harsh, like realistic conditions. But it is still a topic. Some degradations you can't prevent, so they will always be there. And then it's also about how is your maintenance structure. Some companies say we are still the owner of it and we just swap out the stacks every once in a while. But the goal is still to go, I think now it would say 40,000 hours is now sort of the max for these systems, to go higher to 60,000 hours. So what is that, 6 years, 7 years operation before you have to start replacing them. But it is one of the biggest challenges, actually. Yeah.
Hi, thank you for your presentation. I would like to ask about this syngas production by solid oxide cells. Is it possible to adjust composition of syngas to use it directly?
Yes. So that all depends on the sort of the feed composition that you do, steam CO2 ratio, and the current that so the conversion rate that you apply. And then you can tune it almost to whatever you want. So M modulus of 2, M modulus of 3, whatever you want. You can, yeah.
No more questions?
Hi, good morning. Thank you for your presentation. My question will be regarding the water quality. I know on PEM electrolyzers we need very ultra pure water. On alkaline demi water is enough. What about the solid oxide?
Ultra pure water is helping a lot for degradation, especially with these nickel based fuel electrodes. And then it depends on the quality of your demi water and which pollutant is in there. Sulfur is the biggest killer of sulfur, and silicon are the biggest killers, I would say. That's why also silicon or glass ceilings used to be used a lot, and now trying to find alternatives to glass ceiling because it will leach into the electrolyzer, thereby killing the electrolyzer. So we work in the lab with demi water, very nice, clean demi water. Step beyond the above standard one, but we see that also maybe it would be better to get some more ultra pure water in, just to do some benchmark testing and stuff like that. But it is, it's not, some people, some companies say, we can just work with demi-water, but maybe they then have a different solution to take care of these pollutants. Maybe some other gas cleaner scrubbers in front of the electrolyzer.
Well, the use of steam would help.
Sorry?
Using steam.
In what sense?
Together with instead of liquid water, use of steam.
Yeah, well, you always use steam, but still you get your silicates come still with that in gaseous form. Sulfur, of course, stays in there in the first place. So even when you have, that's why you can get away with demi-water sometimes. It's because you already, well, a lot of the impurities don't go into the steam phase, but some do.
Thank you.
Hi, thank you for your presentation. I have just a quick question regarding the efficiency that you talk about this technology. You said it's 80% with the LHV. Is it with the cell itself, or it's included with the BOP of the whole plant?
There is now proven, well, I would say that's hundreds of kilowatt scale, so a module, small module, a container-sized module, that they have reached 84% LHV efficiency for the entire module. Don't go ask me the details, I was not involved in that, but that's what I read recently, that they were able to go to these high efficiencies.
So in your lab, did you consider calculating this efficiency with regarding the all BOP, or the balance of including the balance of the plant, or just with a stack or a cell?
No, if I understand correctly, it was with the BOP. That's what the BOP suppliers that we asked, they supplied those numbers for us, and we integrated with them.
Okay, thank you.
The online audience now is more active. They say, excellent presentation. Can you give us an idea of the cost of the technology per megawatt? So cost per megawatt.
Per megawatt. Cost, no, I can cost per kilowatt, which is more.
Yes,
more,
per kilowatt.
Although I think we should, as a field, step off from the kilowatt, because if you make a very inefficient system, your cost per kilowatt will be very low because you have to use a lot of kilowatts. But to compare, for example, what in the last presentation, it was like practically in Europe 5,000 euros per kilowatt for alkaline. That is also what is calculated for SOE 5,000, roughly around, also in the report we have. But that does not take into account that most of the SOE systems are new. And so they, if you build a new system, one-off system, or one of the first, the amount of extra cost it takes for regulation, for safety checks, for all these other stuff, could easily be 4 times as high, just to build some of the first systems. But if you take that out of account, the cost would be similar to what was for these European alkaline, because stack costs are actually quite low. What we heard from suppliers, they are like, that's already sort of closer to the targets that we have, but it's the BOP, because it's very high temperature BOP items.
So I think I will end with a curiosity, because we have worked in the past with regenerative fuel cells, PEM fuel cells. So what about reversible SOE cells? Do you know any system working and working well?
I think once again it was Sunfire who showcased
Sunfire.
it, but it's not. I'm not sure if that's still a product that they offer in such a way. There is also the philosophy, like, yeah, you can use the same system, but fuel cell operation is 50. If that's 50 kilowatts, then SOE system for the same stack is 200 kilowatts because the voltage is different. Why not just have 2 separate ones? Because then you can actually optimize them. Because they do have some different optimizations. You can use an electrolyzer, you can use for fuel cell mode, but you can't make a fuel cell, solid oxide fuel cell, and use it specifically for fuel cell mode, and then use it for electrolyzer mode, because you need more barrier layers and stuff like that.
So we faced many challenges
but
also.
for reversible, it is for solid oxide. It is basically the fact if you have such a SOE system that you use for it, just putting the voltage lower or positive current, and it works. It works.
Okay, thank you. Thank you again for your presentation. I think we can go for the coffee break. I have something from you.
Thank you.
Just one more question. And about life cycle analysis, do you have an idea if the impact is lower than the other technologies, or you still don't know?
But I'm not really involved in those kind of studies. And I know we do them at TNO in very different departments that focus only on life cycle assessments of everything. You know, there is research being done all over Europe on recycling SOEs and getting the metals out and then just grinding down the. Yeah. I think we also joined a consortium that wants to get one of those projects. And just grind down the YZ and just remake it. And there have been already 2 years ago a project on that. Could be a project that shows it. And you get similar performance if you just reuse the same tools. But it is more complex because it's many different elements, especially for this area controls. It's of course like 4 different
Okay. Let us now start this second session. Before lunch, we have two presentations. We will start with my colleague and friend Nuno Correia, who is the director of the Composite Materials and Structures unit at INEGI. INEGI is one of our interface institutes nearby the Faculty of Engineering. So he's engaged, of course, in R&D in composite materials, and so we will hear you. The floor is yours, Nuno.
Thank you very much. So, good morning. You can hear me, I guess. You never know. A little bit out of this context, perhaps, for most of you. And I wanted to give you some ideas, some slightly different ideas on what hydrogen actually involves beyond the things that you are experts in and the things that you've been talking about in this summer school. So Alexandra and the team here have invited me, I think this is the third time, perhaps, to provide a sort of like a parallel view of other technologies that are involved in hydrogen, and that's the thing that I will talk to you about. So the topic of this talk is advanced hydrogen storage systems. It's not a very creative title. I hope that I can excite you about this topic, and I hope that this works. Yes, I think there's a slight battery problem here, but it's fine. So let's see what the content of the presentation can be. There's a large number of items in this outline. The first of them is how I see the use of hydrogen and high energy density storage, and the reasons why this has had some traction in the recent past. And then we'll go into the context. A few of the things in the context you will probably know, but it will allow me to create a bridge between what I'm thinking and what you've been looking at here. Then I'll try to explain a little bit about what these tanks are. I brought a few examples of really unusual tanks. Perhaps by the end of this session today, you will understand with me why these are unusual and how these are unusual. Then we'll look into materials and manufacturing of composites and the tanks themselves and different types. I will try to go through some elements of the economics of hydrogen storage. So you know a lot about the economics of hydrogen as an energy vector for many reasons, but the hydrogen storage has its own special characteristics. And I'll try to go through some applications and discuss perhaps with you a few things that we've been seeing happening in the recent past, and perhaps draw some conclusions. And I'll try to do this in under 40 minutes and in a relaxed tone with very crowded slides and a pointer that doesn't work always. Nope. Okay, it happens. Very good. So the question that we have with high energy density storage is related to a lot of the things that we think of hydrogen as being useful for. Obviously, hydrogen is important as a storage medium, as a battery in many ways, but we, in terms of mechanical engineering and tanks, we tend to think of this as more related to transportation. And really transportation, because transportation, as you know, is a major driver of greenhouse gas emissions. And so hydrogen for us is a problem of actual transportation and how it evolves in the future. But to have this in vehicles, we need to have hydrogen in a form that is highly dense And so how we transport it is an issue. And then we'll lead into a few solutions that have been explored in the recent past. But certainly, this is related to this conversation. Flying is a big issue. Driving is an immensely polluting or greenhouse gas emission transportation. So all of these things, you know them already, especially if you fly short distance, it's a big problem. That led to a number of initiatives, especially in having hydrogen in many of these applications, in buses, in cars, and more recently in things like trains, in things like aircraft. And perhaps we can discuss a little bit, and I will try to discuss a little bit how the aircraft element is here at the moment. This is one of those really dense slides. You will have all the slides, obviously, but this is a relatively recent discussion, old slide, 4 years perhaps, on why electric-powered cars might be a better solution than hydrogen-powered cars. And in terms of the direct comparison, you've been discussing that extensively, perhaps, with your colleagues. The truth is that that is possibly true if we don't have hydrogen, and the next talk will probably address some of the issues with this. If hydrogen and hydrogen production is an issue, then this leads to the solution that we're seeing today in cars, where you can find lots of electric cars, not many hydrogen-powered cars, because hydrogen is really not available. But in a sense, this talks to a technology that is evolving and that we have to be aware of in terms of how the cost drivers of the technology itself and of making hydrogen available can possibly drive the development of these applications in the near future. I think one of the most relevant recent topics here is that although cars and looking at the near future for cars might be something that is really being taken by electric cars, in aviation, the problem is not easily solved with electric batteries, and it's really not the same problem. In cars, we can deal with having from 1,400 kilograms, 1,400 kilograms to 2,400 kilogram cars, because we have a 1,000 kilogram battery is sort of okay for cars. For aircraft, that is simply not acceptable. And there are no brilliant solutions yet for this. There was an immense drive in the recent years, so this was pushed in the late teens. In 2020, the Clean Aviation started implementing an approach to creating a zero-emission aircraft, with one of the thrusts, as they call them, being a hydrogen-powered aircraft. Their intention was to have hydrogen-powered aircraft entry in service in 2035, and there was a big buy-in from companies like Airbus on this approach. There's actually an evolution on this, is that the technology hasn't grown as fast as they were expecting. There are things in how you actually can transport hydrogen, cryogenic liquid hydrogen, how you can make it available in airports, how we understand the use of these tanks, the use of hydrogen in propulsion, both from the fuel cell side and from direct combustion of hydrogen. So they pushed the entry in service deadline from 2035 to perhaps 2040, 2045. So they gave themselves a few more years to work on this. But the drive to actually make this available to aircraft is a large one. It's a significant one. And certainly this will not be reduced. We see an expansion of the activities in clean aviation on this topic. So what I'm trying to say is this is a technology that we know that we will need. There are a number of building blocks that we still need to overcome, and storage is certainly one of them, especially for applications such as liquid hydrogen and having a mass production of compressed gas tanks. And I've mentioned this before. So I talked about liquid hydrogen. You know about cryocompressed. You know about liquid hydrogen. The focus of what I'm looking at here is mostly compressed gas, compressed hydrogen. But the usefulness of liquid hydrogen for applications such as aeronautical and cryocompressed hydrogen as an intermediate alternative to a few of these applications is still in discussion. Okay, there's been a lot of push in compressed hydrogen and a lot of evolution on that, as we'll see later on. But certainly there's still a relevance in the exploration of both cryogenic use of hydrogen and cryocompressed. It's still very open, and I would welcome discussion on that if you'd like. You obviously have seen this graph a million times, and every time I show this, I'm aware of that. It's just highlighting a fact that we do have 3 different alternatives of carrying the vector itself. We can think of them as relevant alternatives in different application scenarios. And the truth is that we don't know exactly what will end up being in the application, so we need to still continue to develop some of these applications. One thing that I would say is that I find the cryocompressed hydrogen having a very interesting proposition for some really large energy consuming applications, perhaps as an alternative to liquid hydrogen. There are issues with that, but I think it's something that is understood, that was used, that was sort of forgotten. I think it's in a limbo that I would like to perhaps understand why we don't give it a little bit more attention. And this is saying fundamentally the same thing. So densities, volumetric energy densities that will be roughly the same, different problems, different applications that we think that could be coming from these different types of hydrogen storage. So that is the context and the why we're interested in this. So certainly transportation is a major driver. Certainly the different forms of transporting hydrogen are relevant to reduce or abate greenhouse gas emissions. And then the problem with having tanks is how do you actually design a tank? And that is something that I'm wanted to bring to you that is perhaps a little bit outside of your scope, but it's certainly something that is relevant to make sure that we make this hydrogen available in its applications. So tanks, we typically talk about 2 types of tanks, cylindrical and spherical. There's a number of tank shapes and sizes that are applicable to their uses. You are probably aware that the packaging problem of having a hydrogen tank in a car is an issue. One of the things that I bring today, and that you can come and see if you'd like, is what we are doing within space-related programs to develop a compact form of a tank, something that has that occupies volume in a slightly different way. It's still a cylindrical application of pressure vessels in a sense, but there are a number of elements here that make it more compact and more usable in some spaces. And this is specifically not for hydrogen, but for electrical propulsion in satellites where you have a really small space. So you want to take advantage of as much space as you can. So there are alternatives, but even these alternatives do consist of cylinders, as you can see, right? So there's not too much that we can do to get away from that. And cylinders, we can have different dome shapes, and a sphere is a cylinder with a zero-length cylindrical element in it. In our case, that's almost true because we have these domes that we can use. A sphere itself is something that is difficult to package. If you have a lot of space, you can use it, but most of the times we use cylinders because these cylinders are easily packed. So packaging is an issue. Mechanical engineers and engineers that work with with the design of tanks, perhaps learn in their 3rd year. I did. I remember my solid mechanics teacher talking about the three-dimensional state of stress in a cylinder as one of the first examples of a three-dimensional state of stress. And it's really interesting because we have a pressure that is compacting the cylinder itself from the inside. We have a cylinder that is being, the ends of it are being pushed outwards, so we have something that's compacting the metal, something that's pulling it towards the outside, but also if you think of it as a cylinder, we're also pushing the cylinder apart, so the cylinder itself is trying to expand. So in a sense, we have a state of stress, a state of how the pressure actually builds inside the material that's withstanding the pressure inside. That is well understood because we've been doing tanks for many years. Mankind has been doing pressure vessels since the dawn of I would say, steam engines, right? So we understand this, and that was one of the things those were one of the drivers for a lot of the solid mechanics that we learn in third-year mechanical engineering. But in the case of the advanced materials, doing these calculations, and especially doing them in a more refined way, becomes quite complicated. And so we do have a number of ways that we can use to approach the development of these tanks. Some of them are able to respect the geometries of the domes themselves, the overlaps that we find on materials near the boss, the central area. And a lot of those things are taken into consideration when we want to design this. And to do that, we use a calculating machine that is fundamentally a finite element modeling software. That is a dedicated calculation tool that allows us to see in very great detail what's happening at the level of the performance of these materials. And if you want, we can go even a step further. And we can see, in the case of composites, in the case of having fibers and polymers as the fundamental material that withstands the pressure, we can have models that go to the level of the interface between the fibers and the resins, and looking at failure modes, and looking at how this propagates, and how fatigue affects these materials, and how in the case of a fire we have leaks, and how that leads to burst and all that. So there's a lot of quite advanced calculations that can be done nowadays on these materials. We can inspect them in X-ray up to 1 micron levels, and so we can see all of this happening in quite a big detail. So we're quite confident on how we can actually design these tanks, and certainly that's one aspect of actually making these tanks work. There's a number of people in institutions like INEGI and other places that can actually do this work and be partners with you. On the left side, I think the idea there was to have a difference in thickness between a CNG tank, so an 80 bar tank, and a 350 bar tank, I think, or something like that. So what you would see is possibly thicknesses in the region of 2 centimeters of a carbon fiber reinforcement versus something that's much, much thinner than that. And on the top, you have a very strange graph that leads to something like this, in a sense. There's a fascinating aspect of storage. If you like storage and you're fascinated with storage, there's a fascinating aspect with storage, which is that if we reduce the size of the tank, we can reduce the thickness of the wall. And it's proportional. We basically have as much carbon holding the gas, in this case, as we would have if the volume was a single tank, but a larger one. So the thickness in that case would be larger than the thickness in this tank. And ultimately, you can think of, there were some papers a few years back that you probably didn't understand, or I think I didn't understand very well in that time. People suggesting using carbon nanotubes as pressure vessels for hydrogen, which is a very strange idea. But in a limit, you can make the container a very, very thin wall, ultimately a 1 atom thick wall, right? And the principle here is driving the fact that we can use these different tanks to make smaller, conformable tanks, okay? So that is the story of this slide. Another aspect that I think would be an interesting takeaway from today's discussion is the way that we classify different types of tanks. We use these types. It's a very unimaginative way of calling these by a name. There's a type 1, type 2, type 3, type 4, and type 5. A type 1 would be your typical metallic tank. A type 2 would just be a metallic tank with a winding around its cylindrical part. It's a simple thing to do. Mechanically, it's an easy thing to do. And it does take up, that composite layer in the cylindrical part can take up to 45% of the loads. And it's a very simple machine that spreads carbon around that cylindrical bit, okay? A type 3 is a cylinder made of metal where we have composite that goes not just the cylindrical bit, but goes all the way to the top, okay? And in that case, I'm reading from the bottom part of the table. In that case, you have the composite taking up to 80% of the load, okay? So we go from having something that is 45, 50% of the load in a cylindrical case to something that takes up to 80% of the load. You can make the cylinder in a plastic, which is not really load-bearing, but it's just there to take to define the shape where carbon needs to be, and you put the carbon on it. And so that would be a type 4. It's the same as a type 3, but instead of metal in the type 3, you have a plastic in type 4, a thermoplastic, polyethylene or polyamides. And in that case, the plastic is really not there to take up any load. The plastic is there just to define the shape. And so we can say that the composite layers are 100% load-bearing. Okay? But if you imagine this, we still have a polymer liner that does some functions, but ultimately, if we could replace the permeation functions with the composite itself, we could do away with the mass of the polymer liner. The problem with that is, how do you actually make a composite tank in space without anything to constrain it? Right? So it's a difficult thing to do. But if you can do that, it's a type 5. It's a linerless tank. Okay? And I brought you a type 5 tank. Okay? So this is something that shows you that these things are really not just wild imagination. It's actually feasible to do. And ultimately, you can save 10% of the weight of a tank if you do away with the polymer liner. Okay? But doing this requires a number of different steps. And it requires significant, it has to have a requirement for use that makes sense to actually do this. Okay? But in some of the applications of hydrogen that we see today, and other liquid oxygen, in this case xenon, the usefulness of not having a liner is there. So it's still something that's relevant for us. Okay? The application is there. So we can certainly, we start with a tank that's fully metal, and we end up with a tank that has almost no metal, no plastic, nothing that defines the shape apart from carbon itself. Okay? So that's possible. This slide gives you an idea of constitutive components of a tank. A tank is not just a cylinder in metal. There's a number of elements. Some of the most important ones to understand are these bosses, the bosses being the ends of the tank, and the ends of the tank are where you interface things. And where you interface things, in the case of hydrogen, any interface you have, there's a leak. So understanding really well how these things are done is an important thing. So that leak can actually happen in many ways, from the surfaces of the interface areas to the actual ways that you connect the tank to other things. And understanding that is a reasonably important thing. But the elements that you find here, from the boss to the dome section, to those transitions, to the elements in protection that typical tanks have to have when they go into applications, they're all here. The fireproofing, valves that protect it in excess temperature, elements that are used to protect from impact, all those things are part of your tank solution itself. And because pressure vessels are really well understood or have been for many, many years, there's a significant number of standards that regulate these pressure vessel designs. It's one of the things that was most concerning in the beginning of the industrial age was the explosion of pressure vessels. So we do have a number of standards that have congealed in terms of what we can use for pressure vessels. For hydrogen itself, there are a number of standards that are relevant, and there's one specific standard that is really relevant for a lot of the things that we've been talking about. So, ambient testing, fire, hydrostatic bursts, and how it responds to dropping to being dropped, how it responds to fatigue, all that stuff has been looked at within specific standards. So the design of these tanks and having products made out of them actually is very well regulated, and there's a number of standards that we need to comply with to make sure that these things operate as we'd like them to. Some of them are applicable in type 1s, and if you want to transport hydrogen in metal vessels. In type 2s, they're still applicable. In type 4s, least understood, there's the most amount of testing that's required. But certainly there's evolution also in the response of the use of these materials to these tests. And certainly there's also elements that the tests have that we're not seeing here that are important to us. The coefficients of safety that the tests impose on us in terms of use are different from metallic tanks to composites. And these coefficients of safety have a lot to do with how precise historically manufacturing of composite vessels was and how that's evolved. We are trying to reduce the coefficients of safety in a sense while complying with most of these things. So there's a pressure to drive these tanks ever lighter. Some things we see directly by removing liners, or changing liners from metals to plastics and plastics to nothing. But some of them we can't really see in the technology itself. We mostly understand it if we look at how we want to reduce the coefficients of safety, what's required in terms of permanent monitoring in these tanks to be able to use them at a lower coefficient of safety. And all that would reduce ultimately significantly the weights and the costs of these applications, of these tanks. This slide I debated a lot whether it should be here or above, but most of the discussion that I've had with you is composites don't really exist, right? So tanks are tanks and composites are just a material like a metal or a black aluminum that we can use to make these things. But composites, as I'm sure you know, because it's becoming common knowledge, they're man-made materials. They're the most advanced materials for construction that we have today. It's still very expensive. But they provide us with an amazing set of properties. Some of those properties you can see here. So don't forget that this is a logarithmic scale. Composites can have 30 or 40 times more strength per kilogram than a metal. Okay, this is what this graph doesn't tell you very well, but they can. And stiffness, they can also be stiffer than metals if they're used in the proper way. The advantages then go into the equations that drive the thicknesses and the performance of these tanks. You can't see the equations, but there's a symbol there that really just says the stronger your material is, the thinner you can be. So if you can have a material that is 30 times stronger per weight than another one, you can certainly have something that is 4 or 5 times thinner, but still will be 30 times lighter than something that would be made in a typical metal. And it's quite funny that if we look at metals, the strength, so this specific strength, the strength of a metal, the strength is the force or the stress we need to apply it to make it break. That is something that's 20 to 30 times smaller in any high-strength metal to any high-strength carbon. Okay, it's an amazing. So we would be talking about 1 megapascal strength. doesn't matter the units or what it is. And for something that weighs 8 kilograms per cubic centimeter, per cubic centimeter, or something that has a strength of 3,500 megapascal or more, for something that weighs 1.6. So it's really a big difference. These are man-made materials, so they're not there's something to be said about that, as we'll see. The cost in these materials is significantly different from the costs of metals. But what they allow us is to access a number of applications that would be impossible otherwise. Okay. I think I took half an hour. Let's see what I can do with the rest of my slides. A little bit more. It's still late. Okay. So I don't think I'll have a problem with taking an extra few minutes of yours. So this is the ideas. I don't know if I can, no. The tensile strength that you can see there is those are the numbers that we are talking about. From can go up to 5,000 megapascal, which is something in regions that is really exotic. And we can use materials in the form of glass, of carbon, of aramid. They all have different properties. They all have different weights. They all have different ways of being processed. But we can use certainly different ways of approaching building our tanks. And but certainly the message here is, from these man-made materials, we can build things that would not be possible otherwise. And that's why they're appearing in aircraft from the 1970s onwards, today everywhere in everything that requires really lightweight, and some of the only materials that would allow us to actually use pressure vessels for high pressure hydrogen in any context. So we have materials that are basically fibers. These fibers each of them are 7 micron in diameter, and we can buy these materials in bundles of 12,000 fibers to 100,000 fibers, let's say. But they are still thinner than hair, very flexible, very strong, but very flexible themselves. How do we convert that into a tank? Well, we first need to combine that with a resin. A resin is, let's say, a plastic that is involving these fibers and making sure that strength is transferred from one fiber to the next fiber. There's actually different types of polymer matrices that we use, from thermoplastics to thermosets. And all of that has to do with a lot of how do we actually use the materials, how recyclable we want them to be, how high performance we want them to be. But one of the things that we need to do beyond combining these fibers or wetting these fibers in resins is using machines to put them in the places that we calculate are the required places. I told you that we have this way of seeing a three-dimensional way that forces propagate inside the tank. We actually put the fibers in the direction of these forces. We don't put them in mostly any other direction. We use the fibers especially to prevent the tank from changing shape in any way that we can. And we use initially, you can think of this as a machine that rotates a mandrel, a shape, a liner that has the internal shape of the tank. In this case, you don't have a mandrel to do that, so you have a different problem. But if you imagine winding this, having something that's winding, that's rotating this mandrel, and paying out or putting fibers or allowing fibers to be pulled into this rotating mandrel. And if we can make the fibers go into the positions that we want, we can make the tanks of any shape that we'd like. There are other ways of doing this, especially, let's see if I can go back, especially because if you only have something that is rotating, I'll destroy this now, something that is rotating, and you're putting your fibers in this direction, right, and allowing it to be laid onto the material, you will have a large bump in the boss, because you'll have additional material there. And basically, you're compacting all the material in this diameter to something of that diameter. And really that is a problem because you want to optimize that. And because we want to optimize that, we have other types of machines that are a little bit more complicated. So on the top one, you have a 2-axis machine. But we have machines that are able to control multiple axes, robotic machines that can control any direction we'd like. And we can certainly start laying not only materials that are pulled by the winding of the mandrel, but we can also put the materials exactly how we want them ourselves in the liner by having a robot go to the liner and deposit the material exactly as we want them. So the technologies to make these tanks have evolved over the years, and we're ever more capable of doing highly optimized tanks where we control the directions and thicknesses everywhere in the tank. These patterns that you probably see in tanks occur from, that is a very interesting film that shows you how a machine that is 6-axis controlled can actually produce a tank by laying out the material. The rotation, as you can see, slows down as the fiber is put over the dome. And so the rotation is controlled, the angle of the head is controlled, the position of the head along the axis is controlled. Everything is controlled to make sure that we have that layup. But as you can imagine, that layup ends up having a high thickness in the ends that we try to optimize and remove with other technologies. So type 3s and type 5s and type 4s we've discussed. I brought you some examples of that. This slide was to give you an idea that some of the tanks that we've been doing over the years, type 5 that I didn't bring that is in Inesi, actually the top one there is probably a sister tank from this one, that we've been doing for cryogenic materials for rocket launchers and things like that. But certainly there are a lot of other tanks that we've been working on for other materials as well, from type 3s to type 4s to type 5s. And again, some ideas on cryocompressed here. So this slide was just telling you a little bit about the offer that is, or the companies that operate in our universe, let's say. MaHiTech, I think, came out of fuel cells and hydrogen joint undertaking, so that was before the clean hydrogen joint undertaking. But there's a number, so these are companies that came out of European projects, let's say. Some of them have been pushed out, and it's quite interesting to see. But you can buy today some tanks and for some of your applications, which is a very interesting development. What I wanted also to bring to you was this idea, I think the next slides look at the economic aspects of this. This idea of how much does carbon fiber impact the cost of these tanks, and how much is it a limitation for the evolution of this technology. On the slide, on the top left-hand side, the big part of the costs, 70% of the cost is the cost of carbon fiber in a tank. It's still today one of the biggest drivers of costs. It's really difficult to meet the goals of reduction in cost without changing the way we make carbon fiber, and it's still an important thing for a CNG tank. So in the case of hydrogen, it's 70%, a CNG tank, it's 60%. There are ways of actually addressing the cost of carbon fiber, but that's something that's being researched. But it's something that it's still difficult to get there very well. And I think to allow, I'll probably end with this and jump into the questions. You'll get the rest of the presentation. It's fine. One thing that I wanted to show to you was this roadmap. And to tell you how the speed of achievement of the goals of the key performance indicators has been in the last few years. So in 2012, the Fuel Cells and Hydrogen Joint Undertaking did a target roadmap where they imagined that in 2017, so 5 years after that, they would have tanks at costs of 800 euros per kilogram of hydrogen. Sorry. And their volumetric capacity and gravimetric capacity would be 0.023 and 5 respectively. In 2018, so 6 years later, their roadmap updated the costs in 2017 to 1,000, not 800. So that was the reality of things. Costs were higher than they expected. But in 2017, they achieved the 2020 goal in terms of the technical performance of the tanks. The gravimetric density, the gravimetric capacity of the tank was already 5, and they proposed a new target for 2030 of 6. And Clean Hydrogen looked at the results in 2020, so 2 or 3 years later, and in 2020, the 2030 result was already achieved in terms of gravimetric capacity. And so they updated the 2030 to 7. But the cost itself, in 2020, we had reached the original 2017 goal in the roadmap. Okay? So technically, we're able to move quite fast. In terms of cost, which is mostly driven by carbon, which is something outside the scope of what we're discussing here, it's difficult. So the next one would be some applications, and you've heard a lot about this. And perhaps I would just leave that there and have some questions if you don't mind. Okay?
Thank you, Nuno. Questions?
Yep.
Good morning. So I have the obvious question. I don't know. In terms of automotive use, we see that the pressure in the tanks is 700 bars, which is a considerable pressure for this application. And the people have concerns, safety concerns, in case of accidents. What in case of fast rupture of the tank? What can happen? What kind of energy is released? And what are the consequences for the health of the passengers? If there are any comments on that.
I think there's that's a common question. It's not an obvious one, but it's a common question. I'm not sure I'm the specialist to talk about that. I can tell you a few things. First one is the crashworthiness of tanks is something that has been studied quite extensively. These tanks have been shot at. They have been put in fires. There's a number of things that we understand about them. I think there are problems, as you probably know, in where gas escapes if you have a puncture. But if otherwise it's sort of okay, and the temperature is very limited to the region of the jet. There are problems with that, obviously. The question that I typically seen others counterpoint this is if you have a gasoline car, it explodes, blah, blah, blah. There are, I think fire is an issue. And what I've seen is the evolution. So we have thermal protection devices, so valves that would open in case of fire to prevent explosive detonation of the tank. There's evolutions of that. And one thing that I've seen being researched also in that specific field is leak before test designs. So if you have a tank that is inside a fire, if the matrix, if the polymer part of the tank can degrade in a way that you have permeation, you would have a tank that would release slowly the gas, not entirely devoid of explosion, but it would reduce the pressure in a sense. So hopefully there can be some evolutions of that design. That's something I've seen maybe 2-3 years ago, and I haven't seen much more of that. But I think there's quite an interesting approach that can be looked into. Yeah. I don't know.
Thank you for the nice presentation. I had a question regarding the brittling effect of hydrogen on the, well, not on the carbon, because that should be inert, but for the resins and the composites. How well has that been studied so far? And is there a higher chance of leakage for these composite materials than for the purely carbon fiber or even the thick metallic ones?
So perhaps not embrittlement, which is the phenomena that's more characteristic of metals, but there are some phenomena that are relevant for composites in terms of aging of their properties. We can develop cracks, and that can happen for many reasons. And cracking can be micro-cracking, can be just decohesion of the matrix from the fiber, and that can have a propagating effect and can have a significant damaging effect. That is something that's being studied. And this is especially important, if you can imagine, in cryogenic applications, and especially if you thermal cycle them, which we don't want to do, but it's sometimes maybe we need to do, where you have a material that is is under a certain temperature at a certain condition, and if you heat it up, then it expands, and cycling there would be terrible. Fatigue in carbon is not exactly the same problem as in metals. There's really no, fatigue itself doesn't make a lot of sense. But the degradation of the matrix and the life of these tanks is something that we care about a lot. And a lot of these tests have to do with that.
All right, thank you.
Okay. These two more and then one from the audience online.
Thank you for the presentation. One of the most used materials in a physics storage system is magnesium hydride, but it is well known that we need a high temperature to use it, and also absorption and desorption is too slow. So we have been working on some doping method, but we think that technology is more expensive. Do you think that this technology will have some space in the market, or that will be accepted in the market of hydrogen storage? Thank you.
Tough one.
There's an answer in Portuguese to that. I'm more the person of the cakes. So, there was a comedian some years ago that said, that's not really my specialty. But I can try to answer that in a parallel way. I think that there's no fixed solution yet. The reason why I was bringing up cryocompressed is perhaps parallel to what you're saying. In the 90s, cryocompressed was an interesting solution. BMW used it. They controlled the cooling in a better way. The tanks were simpler to do, etc. It was sort of like abandoned in a sense for many years. I think there's still a discussion on where these technologies can actually combine to do what we want them to do in the future. I wouldn't put anything out of the scope. Understanding cost, understanding the performance indicators of these things is an important thing. And as we will perhaps see later on, the availability, or as I was pointing out in the beginning, all of this is driven by the availability of hydrogen in the economy, right? So as long as we have cheap hydrogen, I think there will be space for a lot of technologies. Perhaps some of these will be the first, but I think there will be niche applications for some of the other technologies, and I would find it still relevant to do some research on that today.
Okay.
Thank you for this nice presentation. I have two questions. First one is about average lifetime of these tanks 1-4. Probably it depends on many factors, but can you say more or less how often they should be replaced?
So I was answering a question before. We have to fatigue test them. And we design the tank, we can design, or someone can design the tanks for a fatigue life. Fatigue life would be a useful life that you would like to design as a use case. We've actually been involved in a Type 3 development for 450 bar for 10,000 cycles. So that is achievable, okay? We understand the degradation of the properties in something like that. But naturally, when you design something for a large number of cycles, you need to understand that you have to test it for a large number of cycles, right? Otherwise, we have another Titan submersible problem, which is the opposite problem, but it's, sorry.
And my second question is about this lastest type of the tanks, the fifth one. Do you think that the lack of the liner can be connected with bigger leakage of hydrogen? Is it? Yeah.
Yes.
This is what
That's
I thought.
an issue. Yes. There's a reactivity issue that we need to also take into account. But it's something that you can sort of try to control in the matrices, in the polymer matrices, in the plastics that involve. Obviously, carbon is a ceramic that would be a very good barrier, but the polymer matrices are not. So you can modify them with materials to prevent leakage. And perhaps there are solutions that would be involved having an extremely thin liner that would be very performant. But we would try to get away with doing the tank itself without a liner and then having a small liner.
Okay, now I will take a last question from our audience. Thank you for your valuable insights. I have two questions with reference to the large-scale hydrogen storage integrated with the offshore wind farms.
Okay.
What are the boil-off losses, leakage losses of the compressed hydrogen storage? And is it suitable for seasonal long-term storage for days, weeks, even months? And the second one, what do you think about the geological storage of hydrogen in the context of storing the excess energy of offshore wind farms?
I will leave the second question to Pastor
Yes,
Schwab.
I was thinking the same.
Yes. And perhaps taking the first one, not boil-off, because boil-off certainly is something that's more relevant to cryogenic tanks. But the leaks that we have in these tanks are for compressed gas are not that significant. There will always be leaks in hydrogen, as you well know. So you can calculate the amount of leak yourself. There will be, we can do permeability tests for these materials. We'll know how much the leak would be from the tank itself, from the connections, from everything, and we can just calculate the amount of leak. I'm sure it's more complicated than that, but I feel a bit stressed to finish my my discussion, if you don't mind. But I'm sure there will be other people also that can help with that discussion.
Thank you again. Noon. I want to touch it. I never touched the Type 5. Okay. Okay. Now we have the pleasure to present João Peças Lopes. He came in a rush from another presentation, so thank you for being here. So João is from another institute, INESCTEC, and for sure he will tell us interesting things on integration, interactions of hydrogen on the operation of the electric power system. So the floor is yours.
Okay, so good morning everybody. Thank you for the invitation to contribute to this summer school. And so without further delays, I would like to start by just telling you things that you already know for quite a long time, for sure, that world is presently facing climate threats. And this is leading to a decarbonization of the economy and of the society. And this decarbonization is made mostly through a progressive electrification of this economy, provided that behind this electrification we have renewable power sources to produce the electricity. Of course, this is not the only vector to be adopted. You know that there are other sectors where electricity is not that efficient, that flexible, and in those sectors, another vector, energy vector, that is hydrogen, should be used for this purpose. But of course, that if we think about the production of electricity, we have to understand that this electricity has to be based on the so-called primary renewable sources, and they are hydroelectricity, wind power, solar energy. Here can be either for PV or concentrated thermal power plants, geothermal energy, and more recently with the larger projection in the coming, in the last years and for the coming years, marine energies. So by marine energies, I mean so offshore wind power, wave energy, and also tide power plants, so tidal power plants. So it happens that these renewable power sources, they have a characteristic that they are time variable, which means that it is necessary to use storage energy systems, apart from the fact that other approaches need to be adopted, like to exploit flexibility from the side of the demand. And for this all to happen, we need to put a lot of effort in terms of digitalization of the electric power sector. I would like also to just to show you, perhaps you have already seen this, these are the figures for the National Energy Climate Plan for 2030 and the scenarios for up to 2030. So you can see there that presently in Portugal we have about, well, according to this figure here, it says that we have 30,000 megawatts of installed capacity. We are not that near to this figure. We are more about 27, 28 giga. But anyway, what is important for you to see is that the projections point that in 5 years from now, we will pass from about 27, 28 giga to almost 50 giga, which is a huge increase in installed capacity for renewable generation. And this is going to happen mainly by investing more in solar PV generation and wind power generation, part of it with wind offshore. And we can see, if you look on the other figure from the right side, you can see that the energy that is expected to be produced, part of it is going to feed large projects of hydrogen. And so we are also assuming the possibility of having solar PV generation and wind power generation dedicated to produce electricity to those large H2 projects. So we are foreseeing a power system with a large volume of renewable generation, also large volumes of the distributed generation, and very, very important, a power system that will be characterized by grid dominated by electronic power converters, which is a considerable change regarding what has been the scenario that has been characterized by synchronous machines. And now we are passing to a situation where the grid will be dominated by electric power converters. Well, there is one issue that I'm going to talk in a while, that is with such a combination of renewable power sources in the electric power system, and having in mind that they have considerable time variability, it is important to understand that we may have the possibility, we may have to face periods where we will not be able to supply all the demand, which is something that is not conceivable, right? So the economy doesn't allow such situations to take place. And so it means that it is necessary that the power system, in order to assure the correct adequacy and the capability to have the security of supply, it means that we still need to keep some thermal power plants to be capable to be dispatched when the renewable power sources are scarce, and it is necessary to continue keeping the supply of the demand. And this will be done by using combined cycle gas turbines. They will use natural gas, and so they should be available for this purpose, although they will be used less and less, which means that it is necessary to develop regulatory approach to assure that these units will still be there, ready to operate when necessary. Typically, what we do is that we developed security of supply studies, which are mainly reliability assessment studies regarding the generation adequacy, which means that we have a so-called planning target. This planning target is based in an indicator, loss of load expectation. And in Portugal, this indicator has to be less than 5 hours per year. And this is something that every 2 years, the system operator of the Portuguese transmission system does, together with the General Directorate of Energy. And so they want to be sure that for the next 10 years, they are always capable to have a portfolio of generation capable to assure these planning targets, like the one of the loss of load expectation less than 5 hours per year. Well, but we have a climate law also that says that by 2040, we need to be about almost 100% decarbonization in the electric power sector, which, as you can imagine, requires some creative approaches. And these creative approaches are very much related with the way how to storage that energy, because what we are going to have is that with this combination of generation sources in the power system, we will have many periods of the year, many hours of the year, where there will be a surplus of renewable generation. So there will be no load to accommodate the generation that is taking place. So the idea is to use storage. And of course, we are lucky in Portugal because we have about 3.8 gigawatt of reversible hydropower plants, which means that they are already capable to make a lot of storage, hydro storage in this case. And of course, added to that, we may have battery energy storage systems, but mainly hydro storage systems are the most important tool to deal with that. But even with this approach, we will have a lot of energy that will not have demand, and which means that it will be curtailed. So our idea is very much based on the concept of seasonal storage, which, by the way, was the question that was made before. And so in this seasonal storage, as I'm going to show you, our idea is to develop the concepts related with power to power. So which means that those surpluses of renewable generation, electric renewable generation, will be used to produce hydrogen with the electrolyzers. This hydrogen will be injected in salt caverns. And let me tell you that in Portugal we have structures that allow for a very large capability of storage of gas, or natural gas. By the way, let me tell you that the Portuguese transmission system operator and gas operator already uses those caverns to store natural gas. So the strategic volumes of natural gas are already stored in those caverns. But the idea is to make the repurpose of these caverns also to be capable to store hydrogen. And then use turbines that will burn the hydrogen and will produce electricity and inject it back into the grid. So this is a solution that is popping up. So Siemens, Mitsubishi, they have already developing these solutions. So this is not a futuristic thing that we are aiming. No, it's something that is already at the corner. And so it is possible to develop this solution. For this purpose, what we did was to develop a methodology to try to identify how much electrolyzers are needed, how much H2 power plants are needed, how much storage is needed to support this concept of the power-to-power to deal with the seasonal storage. So what you can see there is the approach, as I said, we developed it, and it is based on sequential Monte Carlo simulation, chronological Monte Carlo simulation, which means that we are assessing the reliability of the power system by just checking about the loss of load expectation indicator. And if it is less than 5 hours per year, it means that we have to assume that we will install so the H2 power plants, and we will try to increase step by step the installed capacity of these H2 power plants, such that we are capable to keep the target of 5 hours per year. So, of course, these H2 power plants are fixed ones, and so that's what we do in a loop until we get the value of the 5 hours per year. Having identified the installed capacity, then we try to see how much should be the installed capacity in terms of electrolyzers, and then once we have the installed capacity of the electrolyzers and also the installed capacity of the H2 power plants, we are also capable to identify the volume of energy storage for hydrogen in this case. And of course, then we have a block of assessment very much related with the definition of public policies to deal with this. So we need to identify what should be the public policies for these ideas to be developed. And very much important is the regulatory approach that will support the development of this solution. And by regulatory approach, I am very much concerned with how we are going to remunerate this solution in order for the investors to put money in such solution. So, and of course, this to happen in the future. And this is very important to understand that investors, they need a stable regulatory framework, otherwise they will not invest. And it's also very important to learn and to realize that something that we want to happen in 5-6 years from now, we need to take decisions today. To take decisions today to clarify the regulatory framework. Otherwise, what we are aiming to happen in 5-6 years from now will never happen, because there is not a stable regulatory framework. So, and this approach is very much oriented to try to identify the solutions from the technical point of view, but also the economic and regulatory framework approaches to be adopted. Well, how do we do this assessment of the reliability? So here I'm just showing you the approach that we follow in terms of chronological sequential Monte Carlo simulation. So what we do is that we run hour by hour the operation of the power system with profiles of renewable generation, so wind power, solar PV, hydro, and so on. We also know the profile of the demand for the coming years, and for a specific year, let's say, for instance, 2030. And what we do is that we sample the state, we access the values of the renewable generation, and then we do the generation dispatch, because not all the renewable generation may be able to supply the demand, so you have to do the dispatch, taking into account also the hydro resources and the thermal power plants. And we then evaluate the possibility of having load curtailment. You can see on that picture over there. So just an example of the way how load is evolving, the way our load capacity, our capacity of generation is available. And if the capacity of generation is below the demand, it means that you have load curtailment. And in this way, we are capable to evaluate the reliability of the system in terms of the capacity to supply the demand according to several load profiles, even considering a probabilistic modeling for load and for the renewable generation. On all this simulation, we also take into account unavailability of the power plants, because they may be out of, they will be, so they may have, they will be either having an outage, or because they have a malfunction problem, or because they are in maintenance. So all this is taken into account. We use for that a two-state Markov model for every power plant in the system. And so we also take into account the net transfer capacity, which means that we are considering the interconnection capacity between Portugal and Spain in this case. And so we do all those simulations taking into account this type of chronological simulation. So this is just a description how we size the fixtures generation unit, what we call the green H2 generator. So we perform and we try to calculate the loss of load expectation of the static reserve and the surplus of the renewable energy sources. And in this way, we are capable to identify the installed capacity for the H2 plants. And once we are capable to supply all the demand, so we stop, and in this way, we are capable to identify the installed capacity for these power plants. Just to show you that this is the minerals, a picture with the mineral salt structure caverns in Europe. This is from a paper, Caglian, 2020. This is a recent paper, and you can see that there are several of these mineral salt structures in Europe, and in Portugal we have a considerable capability to store these gases, and in this case hydrogen. As I said, the Portuguese system operator of both electric transmission system and natural gas system, they have storage of natural gas at the moment already there. So the idea is just to change or to use available mineral salt structures of this type to store hydrogen. So for the H2 storage dimensioning, we use a very well-known equation that shows the way how the energy that is stored is going to evolve in time, step by step, according with the moments where we have the electrolyzer producing hydrogen, and then therefore meaning that they are injecting hydrogen in the cavern, or when there are moments where the H2 power plant is operating, which is extracting hydrogen from the cavern. And in this way, we are capable to visualize the way how the storage capacity is going to evolve along the 8,760 hours of the year. So in this way, what we do is a chronological simulation of the generation system together with this storage capacity. Well, this is just to show you what we are aiming in Portugal, because we have an old combined cycle gas turbine plant with about 1,000 megawatts that is already too old and is about to be decommissioned. As a matter of fact, they have prolonged the operation of this power plant because of security of supply problems. But we have to identify another solution, and the other solution will be to make the repurposing of this power plant also to start burning hydrogen, and in this case to use it as a kind of a pilot. So we are capable to use at least, if not all the turbines, at least one of the 3 turbines to be a pilot to test the feasibility of this solution. So what you can see here, this is the demand along the year in Portugal. So 52 weeks There you can see there are the 52 weeks of demand. And also, we are identifying the potential of renewable energy that is curtailed. And what you can see there is a very simple and interesting thing, is that we will have a lot of curtailment during spring and during summer, just because during spring there is a lot of wind, and during summer there's a lot of sun. And so with the potential, the installed capacities that we have already in Portugal, that's what it leads. So considerable amount of curtailment during spring and summer, and it may happen that we will have a shortage of renewable sources in late autumn and winter, just because the demand is larger. As you can see, the demand there is larger, and you may have days where the sky is covered with clouds, where there's no wind. And so in these situations, there is a problem of scarcity of renewable power sources, which means that we may put in risk the capability of continuing supplying all the demand in the system. So we have done these calculations and these simulations for 2030, 2035, and 2040, and we can see the way how we foresee the evolution of the curtailments along the year. So curtailment is decreasing just because the demand is supposed to increase. Because there are a lot of industrial projects foreseen for Portugal, for hydrogen, for ammonia, also for data centers, large data centers that are foreseen to be installed in Portugal. So it means that with time, this curtailment is supposed to decrease. But anyway, there's a large amount of renewable energy that will be curtailed, and this puts also in risk the feasibility of the investments of the companies that are deciding to invest in solar PV plants and wind power plants. So that's why we need to look carefully at this problem and try to find solutions. And one of the solutions is exactly this one, is power to power, is develop a power to power approach based on a seasonal storage strategy. And you can see there, we are, can I? Yeah, fantastic. So the H2 plants are supposed to operate here. So exactly in the moments of the year where I already mentioned that were late autumn and winter, which are the moments where there is more scarcity of the renewable resources regarding the demand, the way our demand evolves. And so it means that is there where we are supposing to operate these power plants. Of course, these power plants are going to operate rarely. Well, let's hope they do it this way. But anyway, we are still assuming from simulations we did that we will need about 0.8 terawatt hour of energy to be supplied to the system through these power plants. Which means that assuming that we have an overall efficiency of about 40%, it means 2 terawatt hour of energy that we need to get from the power system, and in terms of avoiding curtailment, renewable energy that is avoided through curtailment. Of course, we did lots of simulations. We did simulations for 2030, 2040, and so on, and assuming different interconnection capacities, because this is very important. So all these studies are very much dependent on the net transfer capacity that we may have with Spain, which means that we are modeling also the Spanish network. And so we have assumed different combinations of installed capacity for these power plants. And typically what we arrive is that conclusions that these power plants, they may have about between 1,300 megawatts to and 400 megawatts. But obviously it depends on the net transfer capacity that we are considering. We did, as I said, similar analysis for 2035 and 2040. As I said, what we get is that with this approach, we are capable to keep the loss of load expectation reliability indicators below the 5 hours per year if we adopt this approach. Of course, as I said, there are complementary problems. So the optimization of the electrolyzer capacity sizing, the dimensioning of the storage, the remuneration solution, the definition of public policies. I don't have time to cope with that because I also would like to show you another way how electrolyzers can be used to help the operation of the power systems. That is, as I presented you, this was one vision of the support that electrolyzers can bring to the power system. And under this approach of seasonal storage and with a power-to-power solution. And in this case, so the electrolyzers and the hydrogen, they are helping the power system in keeping security of supply. Now I'm going to also show you how the electrolyzers, they can be used to help operational security. So the first part was security of supply. Now I'm going to talk about operational security or stability, if you prefer. What do I mean by this? Is the capability, the robustness of the power system to be capable to support incidents, disturbances in the grid, and to be capable to respond when those incidents take place. And what we have done was just to see how electrolyzers, since they can be modeled as flexible loads, how they can help in frequency control. Because in the electric power system, frequency is used to evaluate the equilibrium that exists between demand and generation. And the power system has always to be operated under this equilibrium. Demand should be equal to the generation at any moment. So for that, we developed studies, especially in Iberia, so Portugal, Spain, and the way how, if a problem, an incident takes place in Iberia, how this will behave, having in mind that the Iberian system is interconnected with Central Europe through overhead lines that cross the Pyrenees, so between Spain and France. So, by the way, this is very similar in terms of problems that can be addressed to the blackout that took place in the Iberia on the 28th of April. And so we already did some simulations with our model, and we were capable to reproduce exactly what happened in the Iberian system in that day of the 28th of April. So what we have here is that we model each of the systems with a single bus, a single node, where all the technologies are connected. And at the same time, we assume that we are also connecting the electrolyzers, and we have the model of the electrolyzer here. You can see it here, the way how, very simple, the way how the electrolyzer is responding. This is mainly the control loops that we are considering in terms of response proportional to frequency deviations or response proportional to the derivative of the frequency regarding time and so on. And so we are just taking profit from the capability of electrolyzers to respond. Of course, we have different responses according to the type of electrolyzer. So if it is a PEM, it will respond much faster. If it is a solid oxide electrolyzer, it's different. If it is an alkaline one, is more so. No, the dynamic is not so good, while the PEM is much better. Okay, and so what we did was to check the capability of these electrolyzers to respond, and what you can see there, what you can see is that once we have the electrolyzers participating in frequency control, we can have a reduction of the nadir of these excursions. This is an excursion of frequency related with a sudden loss of generation. So what we simulated was to lose about 3,000 megawatts, which was, is quite big already, but it was not what happened on the 28th of April, which was much larger than that. But anyway, 3,000 megawatts is already a big incident, and what we simulated was just to see how the Iberian system was behaving, assuming that we have electrolyzers participating with different values in the frequency control. And obviously, what we got was an improvement in the behavior, in the dynamic behavior of the electric power system. So it means, therefore, that the electrolyzers are capable to help the response of the system, and therefore we may think that they are capable to provide what we call ancillary services. And if they provide those ancillary services, it means that they should also be remunerated for this. So we are also thinking on the way how to remunerate additionally electrolyzers when they are capable to operate in this way. Just to show you, okay, we did lots of simulations, but we wanted to see if we were capable to have the similar responses with a real electrolyzer. And this is what we did. So we dived into the world of chemistry and electrolyzers. And so we bought an electrolyzer of 8 kilowatts, is there, a PEM1, and 5 kilowatt is a 5 kilowatt. There's the stack over there. And what we did is that we developed all the power electronics, so which means that we have a stage passing from AC to DC, and then we have two other stages, DC to DC and DC to DC, just to control the ripple and to be sure that we have a very steady voltage that is applied to the stack of the electrolyzer to avoid fluctuations in the power that is consumed by the electrolyzers. And with this, we were capable to include the capability of the electrolyzers to respond to frequency excursions. Okay, so, and the results were very, very, very interesting because we were capable to see that we did simulations with the theoretical models, and we got the real world results from the PEM electrolyzer, and they matched quite well. So it means that what we were conceiving was indeed possible, and it shows that the electrolyzer can be used to deploy what we call frequency containment reserve, which is participation in primary frequency control. Obviously, for those that are electrical engineers, they know what I'm talking about. For those that are not, it's more difficult, but it's also necessary to bring frequency back to the 50 hertz, and this is a task of the so-called secondary frequency controls. And for secondary frequency control, the electrolyzer is even much better in performing for those situations. So we were very, very, very happy with these results. And, oops, oh, no, I wanted to show my last slide. Okay. But before that, let me just tell you another thing that we did. So we also developed the power electronics of the converter that we developed. And by the way, we have now a patent regarding that. That is, let's assume that in a few years from now, we may have in the Iberian Peninsula, a fleet of electrolyzers that is about several gigawatts of installed capacity. If there is a short circuit in the grid, so voltage will drop in the system, will propagate through the buses of the system, and what it may happen if we don't take measures in advance is that suddenly we will lose a lot of demand from the electrolyzers, that it may go up to gigawatts of electrolyzers suddenly disconnected because of short circuits that may take place on the grid, and the residual voltage propagates around the point of where short circuit takes place and suddenly disconnects those electrolyzers. It means what? It means we have a huge imbalance on the system and a big stability problem in the system. So what we did was to impose for those electrolyzers not to be disconnected, which means that they are capable to ride through the faults. Okay, so, and this is something completely new that we have already developed. This is a patent that is pending now, and we are capable to have, through power electronics development, we are capable to have the electrolyzers participating in these frequency regulation services, ancillary services, and also providing fault ride-through capability. And just to conclude, just to remind you that indeed we believe that electrolyzers and hydrogen, they can be used to help the operation of the system in terms of security of supply through the so-called power-to-power approach, and in this way providing seasonal storage in helping the operation of the system. And like that, I close my
Thank you.
contribution, which I suppose
Thank
is
you.
on time.
It's on time. But of course, we will still have, we have to do some questions.
Yeah, yeah. Please feel
So,
free to
feel
make any
free.
questions. I will be happy to try to answer them. And thank you for your attention.
First one.
Thank you for your presentation. I made me a more general question regarding the Portuguese or Iberian grids and the increasing grid capacity needed for all the electrification. How is that over here? Is that facing struggles? Because in the Netherlands at the moment, grid congestion is the name of the game. And we have to
Yeah.
wait 10 years for current companies to be attached to the grid.
As everywhere.
Okay.
As everywhere, I mean, there are problems related with the capability of the grid to be available to supply from one side the demand and to accept the generation from the other side, so the hosting capacity. Yes, so the same problem happens here. Of course, that what we are trying to do is that we are trying to change the traditional approaches used by system operators when they do planning, that is very much based on deterministic rules of the n-1, and we are trying to convince them to change this. I suppose this is going to make its path, and it's going to also, they will arrive at the moment they will have to accept it, because there's no other way. Otherwise, you will have to put more and more and more infrastructures, transmission infrastructures, and many people say it, not in my backyard.
All right, thank you.
Okay.
Thank you. Before Ruineto, I will profit from the
There's
audience.
another question over there.
Yeah. From the audience online.
Okay.
The current efficiency, great presentation, the current efficiency of power to power is close to 40%, which is far less than battery energy storage.
course.
Do you think the hydrogen power to power is a viable option, and why, in the context of developers' willingness to adopt it?
Yeah, I fully understand your question, and it's a very timely question. Of course, that if you think that in hydropower plants we are capable to get round-trip efficiency that can be even larger than 90%, and in batteries you have 85%, you may say, so 40% is really short. It is, in fact. But if you think that what you are doing is avoiding curtailments, so what we are suggesting here is to avoid curtailments, and of course, also considering that this is to generate electricity only for a few hours of the year and for a small number of moments, so it makes sense, because in this way we are contributing to a full decarbonization of the electric power system. Of course, that there is one thing, that is how we are going to pay for this. So the payments are based on the so-called capacity payments, so which means that they are based on the availability of this infrastructure to supply that demand whenever necessary. They are not going to operate in market, by the way. They are not supposed to operate in market. They are going to be operated by the transmission system operator that decides whenever it is necessary to use these plants. But of course, I understand the question, but please understand that we are just trying to reduce the amount of curtailment, and in this way also bringing feasibility to the economic business projects of some investors. We are contributing for that. Okay?
Okay, thank you. Rui?
Okay, congrats about your very clear presentation. My question is also in the same length of the costs. You know that the hydrogen lives from very cheap electricity, and not electricity is also power grids and power taxes. You know, even if the electricity cost is very low or zero or negative, we still have to pay the grid transmission and the infrastructure. So if the electricity becomes very cheap, the grid costs can represent 50% of the cost of the total or more of the energy. And there is also an issue is regarding to the hydrogen cost. If the hydrogen electrolyzer operates half of the hours per year, also the levelized cost of hydrogen will double. If we use just a few hours, this cost can be, the operation cost can be very huge. How can you just just apply this to the only a few hours per year? If you have to pay, this hydrogen could cost very high to do this.
Thank you for the question. Yes, indeed. So you will have large costs of operating those power-to-power solutions. But what you need to do is also to compare these costs against what we call the VOL, so is value of loss of load, okay, which is huge. So the comparison should not be made in terms of price markets, but against the value of loss of load, of so supplying load, okay, which is thousands of euros per megawatt hour, things like that, okay, and then it's, I mean, this solution is much less than that, okay.
Okay, and we have time for the last one. Then we will go for lunch.
Yep.
Good afternoon, Professor. It is a pleasure to see you again. So, point number one, the remuneration of the installed power over the years is the first aspect I would like you to elaborate a little bit more. The second aspect about the curtailment, I won't discuss that, but the ancillary services, they pay well, the investment.
Very much.
So that's the second aspect. And the third aspect, which for me is a big curiosity, because we have the, how do you call it, Comunidade Intermunicipal Médio Tejo, as an European, how do you call it, European hydrogen valley, exactly. If you are studying with them, one off, not the two, one off, or if it is to decommission everything and to put a new one, a completely different one from GE or whatever, a small turbine. So,
but for the turbine, you mean?
Exactly.
Oh, okay.
It's a curiosity.
It's
I told you, the last one.
So the first question was, sorry, was on
installed power remuneration.
Ah, okay, yeah. So the idea that we developed, and by the way, we studied the different types of remuneration solutions, like so rate of return, well, 3 or 4 remuneration approaches that we have studied, and we came out at the conclusion that the one that was indeed the less costly for the system was the remuneration through capacity payments. Yeah, and which is something that European Commission is, I mean, not promoting happily because they would not like this to happen, but they don't have another way to do it. Spain is now assuming that this is inevitable, and we will have to adopt a similar approach because if it is not for hydrogen power plants, it is for natural gas power plants that will only operate, is the same exactly. They only operate less and less hours in the year. So that's what we did. And again, we tried to internalize all the costs in the model that we developed. So the cost of investment, all the costs of even repurposing the caverns to be capable to accept the hydrogen when used in this way. And we even identified a value for this remuneration. I don't have it here. I can give you a paper that we published, last year already, about that, where we are describing the approach that we developed. Yeah, regarding the ancillary services, as you well said, ancillary services are very well paid. So it's, many plants, many generation companies, they take a lot of profit from ancillary services, and they don't get the right remuneration on the daily market. They are going to take it on the ancillary services markets. So that's here a huge possibility for electrolyzers if they are capable to participate in these, not on the primary frequency control market, because it is on the secondary, exactly. On the secondary, there's a huge possibility of getting good money there. And regarding the hydrogen valleys, well, we are not involved in that. What we did is, this is within the so-called Green H2 Atlantic project that you may have heard about. This is a project that is where EDP is the leader of the project. The project has been suspended, by the way, yeah, but is now restarting again. Yeah, let's hope so. And then I don't know exactly who is going to be the company, the manufacturer that is now going to supply the electrolyzer. Okay, but I don't know. I don't know what. I don't know which is the company that won the first bid. Yeah, it was McPhy. It was McPhy at the beginning, but McPhy is left, is already out, and so. But I don't know who is going to be the next participant in the project on that case.
No, we are
Okay.
One of the two.
Okay. So with that, it was quite a.
Okay.
Was really, so there is no participation of you in Nestec and
No,
Netherlands?
no, we are not. Yeah.
Okay. Thanks again.
Thank you
for your great presentation.
Thank you for your attention.
And then it's for you. Thank you. And so let's go for lunch, and we will restart around 2.
Okay.
Thank you.
So, good afternoon. I hope you have a good lunch. I have again the pleasure to receive Paul McCormack from Hydrogen Ireland today, giving thoughts on Green Data Valley. Okay, so the floor is yours again.
Obrigado. Alessandro. We will get there. This time tomorrow. Ladies and gentlemen, thank you. We will continue in the same context as yesterday. Hopefully with more questions from the audience, less questions from the older members of the audience, the younger members, without being ageist. Outside of my professional work, I coach football, Irish football. And one of the things I like is about meeting people, and one of the things that teachers or lecturers cannot do is give people confidence. That's the biggest barrier we have as society develops, the lack of confidence. Not just confidence in doing things, we were having this conversation over lunch. The confidence in driving change and the confidence to stand up and say, we need to do something different. And today's talk or workshop is about what we're working on in Hydrogen Ireland, green data valleys. We talked yesterday about hydrogen going beyond just an energy force, how we can use hydrogen for catalyst for change. And when people talk about sustainability and carbon footprint, they see that as a constraint. So for anything that's bad for the environment or too much carbon, we should stop. But instead of saying we should stop, we should look for alternatives. So instead of thinking of sustainability as a constraint, we should look at sustainability as a catalyst for better design. And then look how we adjust. And then as we look at the two most powerful forces in our modern world, data and energy. Post-COVID crisis, Ursula von der Leyen had talked about the growth of, we're missing one. Ursula von der Leyen talked about the growth of Europe post-COVID. And the two recovery pillars she talked about was clean energy and data. They're not separate, they're interchangeable. So how can hydrogen play a pivotal role in making data infrastructure sustainable and future-proof? And how when we look at 6 different sections of today's workshop, again, if you don't understand my Irish English accent or I'm talking too fast, don't hesitate to stop or ask a question. All of the slides will be circulated. There's also another paper, the same as yesterday, will be handed out to you. And I want your feedback. We had some feedback last night, was excellent, some signposting last night from some of the audience. And it's about that interchange of ideas. So how do we frame the challenge? What's our thoughts, your thoughts? What are green data valleys? My interpretation of them and what you think we could adjust or change. What are the pillars of sustainable data? The role of hydrogen, barriers to solutions, and then a call to action. So how do we look at what is an explosive growth of data? If I look at the two gentlemen here on the mobile phones, sending messages, right? The power for that has to come from somewhere. How many people save photographs on their phones? Never to look at them again. Years ago, you would have printed the photographs off and threw them into a drawer or a box. And they sat there. But they sat there without having a parasitic load on our environment. Every piece of data you save, every piece of useless photographs, you don't delete. They're being stored on a server somewhere in the world using energy. And we've got used to that. Has anybody cleaned out their emails in the last 2 months? Is that honest? Now, you've been honest putting your hand up? Therefore, you have a social conscience. Either that or Microsoft sent your message, you're running out of space, buy some more. So that's the message they send you. They don't say clean up, they tell you to buy more. So you have all this storage that you're paying for material that you may never use again. And that data is exploding and getting worse because we're lazy in nature. We keep moving things ahead. But one other thing is we've become perfect. The photographs you used to take with your old camera somebody with their tongue out, their eyes half closed, or they looked half drunk, you still printed them. But now we delete those. We only want to show photographs that are perfect. And that's society's drive and how we now move forward, or how we think we should move forward. And how we look at green data valleys. It's going to take an energy to power this. But if we keep powering it the way we're doing, it's not sustainable. So here's the conundrum. And it's the paradox. AI and cloud services are going to grow exponentially. So do their emissions. So in Ireland, they've said no more data, no more data centres. And why do you think they said that? Any thoughts why they said that? That's part of it. Keep going, expand on that. Oh, no, nothing got to do with privacy. This is Ireland you're talking about. The answer is lack of planning. We have a grid that's saturated. We talked about this yesterday. I know all these data centres want to come in, and there's no room for them. There's physical room, but there's no energy room. So the government answer is no more data centres. So in 5, 10, 15 years' time, when all of those data centres have gone to Sweden, Norway, Morocco, and other countries, those countries are going to benefit from the jobs, the spin-off, and the growth, whereas the countries that say no and close their borders will suffer. So that's the paradox. The more data we use, we have to fight the climate change, the more emissions, and we have a larger digital footprint. So how do we then tackle that? Our workshop objectives. Let's understand the data energy impact, explore hydrogen solution, and then identify other pathways. So which of the three, insight, strategy, and action, do you think is missing from the public discussion? 3 things. Hands up who think insight. No. Strategy. Action. With no hands up at all, so nobody thinks. If we look at the lack of strategy, the governments in all of the different countries that have been inundated with data centres don't have a strategy to move forward because they've been caught in the wrong foot. The energy goals, the energy options they have are limited, and their strategy is not fit for it. So data's hidden costs. By 2030, data centres could consume up to 8%. In 2023, data centres in Ireland consume 21% of Ireland's electricity. So over a fifth of Ireland's electricity. But if we take data centres out, without data demand, Ireland's electricity need did not grow. So take that into your head. There's an opportunity here. Something's growing to demand. Domestic energy didn't grow. The demand for domestic didn't grow. So that conundrum, 21%, and that's only going to set to grow. So without data centre demand, Ireland's electricity was static. But Ireland grew the second largest rate in the EU, 25% of electricity demand, powered by the demand for data centres. And that scale has now grown to where the government have now said, right, there's no technology headroom, there's no headroom, put a stop on it. Rather than saying, right, let's look at alternatives. So if we look at data centres as flexible grid assets, we touched on this yesterday about sharing the load, bringing loads on and off. If we look at a flexible grid asset, how do we adjust the power in real time to balance supply and demand? Data centres store the material all across the world, and there's 3 different levels of access that they require. So the information that you require now in Portugal goes to a Portuguese data centre in the peak time of the day. Could that not go to another data centre that's not at peak time? So it's about sharing the power load, sharing the power demand, and using the smart tools that we need and that we have to move that forward. Data centre valleys. If we look at Europe, what they have coined is the hydrogen valleys. Based on the Silicon Valley in the US, they're now looking at hydrogen as green. We've taken it a step further and looking at how we use geographic or virtual hubs where data infrastructure operates within planetary boundaries powered by renewable energy, zero waste and community benefit. And how do we create an ecosystem based on clean energy where data centres then give you that opportunity that you require? Where you're able then to look at the clusters, and if you look at historically, there's always different industrial clusters around the world. How do you start developing an ecosystem to support a data cluster? Where you have clean energy, and then you look at the valley as a system, which is circular design meeting that demand. It's not just one technology or one solution, it's a system of systems. So have a think of a data center as a living, breathing organism. It needs food, which is energy, water, temperature regulation, and waste management. Translate that now into a closed loop where your power is clean, the waste heat is reused, the cooling is optimized, and the entire system is interconnected for efficiency and resilience. So you're back to that circular economy we talked about yesterday. We're now talking about a closed loop system where, just the example I give there in Chile, it integrates solar power, green ammonia, and port-export infrastructure, all within one ecosystem. And it's not just a pilot, it's designed to produce 1 million tons of green ammonia. So there are solutions out there, there are options to look at, and we then look at pillar one, that bit of renewable energy. How we look at microgrids, power purchase agreements for the data center alone, not in isolation, but part of that. So solar here and in Ireland, solar and wind are central, but they're intermittent, which means we need a bridge to that intermittency, and hydrogen can act as that battery. Storing energy, feeding it back during high demand. And the renewables is the critical bit, but the intermittency has to be overcome. That's where hydrogen is the solution. If we look at pillar two, the cooling innovation. In your data center, rethink your thermal loads. Up to 40% of your current energy use in data centers goes to cooling. But if we are smarter, we can cut that waste and then bring the cooling to 34% of that data energy use and slash that. If we look at liquid immersion baths to seawater and geothermal cooling, one of the examples you give later on is in Norway where they have it in a mine. But if you look at the seawater we have, look at the access you have here in coastal regions, how you can use that as your cooling mechanism rather than using energy. Liquid cooling, Nordic regions are using ambient air, and cooling continues, 40% of that energy, but nature offers those solutions. Facebook's Swedish center uses Arctic air, and it cuts their cooling and major energy demand by 50%. So geographic solutions, geographic opportunities, back to where we talked yesterday about hydrogen topography, where the options are, where we can harmonize those. Pillar three is then now start looking at our hardware. We've looked at renewable energy, we've looked at energy efficiency, so how do we do more with less? If we look at chip efficiency there in Intel, how that modular server now has dropped over the years, their demands. So we optimize hardware and software, means that we reduce the temperature at the source, use efficient AI models, lean algorithms, and edge computing to cut unnecessary load. We talked earlier about that load that you have with your fixtures. A lot of that's not been used, so there are unnecessary loads that can be removed. So do we nearly read models that are 10 times bigger or just twice as smart? And then start devising that. Look at the efficiency, not just about hardware, it's about the orchestration of smarter chips, virtualized workloads, and AI load balancing lets us do more with less. In AWS's gravitation chips, they've cut the energy need by 25%, and refurbished servers extend hardware lifespans by 3 to 5 years. So it's looking at that hardware efficiency, reusing new chips and new opportunities. Pillar four, then looking at policy and standards. How different rules such as the EU Climate Direction 2030, climate tax incentives, instead of climate fines, take those fines and front load them to make them incentives. Again, it's only a move in legislation. It's not a major move of people, it's a stroke of a pen. By changing the deadlines and changing the aims, so instead of carbon fines, make them carbon incentives. and use that policy lever for smart regulation. Singapore is supposed to be the smartest. They also, like Ireland, have a moratorium on data centres because they don't have the energy. So we're not alone. We're not the most nascent government in the world. A lot of other governments are caught in the headlights and are distracted with energy need because they've already got their goals. So with that policy that we talked about yesterday, how do we shift that? How do we inform that? And then why hydrogen? As we've talked about the intermittency and the need for continual power, hydrogen is that bridge between your clean supply and your digital demand. Now, not just for data centres. Your hydrogen is an energy store, short-term, medium-term, long-term, either in pipes, tanks that you saw this morning, or in the salt mines. How we now look to redevise and re-option. One of the things I looked at this morning, we're working in tanks as well, the shape of a gas tank has never changed, has it? Go back 40 years when you bought your gas in a bottle. It has the dome top and the dome bottom. And the structure is still much the same. So how have we learned from the past and now move into the future? If we look at where hydrogen turns into flexible power, when the sun shines and wind blows, we have power, but when we don't need it, instead of losing it, and as you said yesterday, costing up to 140 million in Ireland alone in curtailment, how do we store it? So how do we see those collective hurdles that shape the solutions as we focus on what next? Hydrogen stores that intermittent renewable energy and delivers it back on demand when we need it. It turns our peak power into solar or wind, and that for carbon-free power. To our grid challenges, many parts of Europe, including here and in Ireland, we have grid saturation. It was mentioned this morning about the brownout when the power dropped. I may be wrong, but it was a flexible load in another country caused the blackout here. So that's some of the grid challenges. We're lucky enough, we're an island. If somebody turns the light off in Belfast, it doesn't go off in Dublin. So how do we look at the grid and look at that regional opportunities where hydrogen takes away the strain on the grid currently? Because it's going to be 15 or 20 years before any major infrastructure is built. So the short-term solutions such as hydrogen take that strain away, enable what I call off-grid computing, unclog the grid system by using hydrogen as a buffer, and relieve that pressure to enable these decentralized data clusters. We talked yesterday about the curtailment in Ireland. It was 1 terawatt hour of renewable curtailment this year alone. And that equates to 140 million of lost opportunity. And that 140 million lost opportunity is not the system people paying for that or the producers, it's the consumers, because it's in your bill, it's in our bill. Well, they're paid for curtailment. You're paid to produce, and if the grid doesn't want it, you're paid to curtail. And in the future plans of the 5 offshore licenses that were granted last year in Ireland, curtailment costs are built in. And that's the difficulty we have. Grids are not designed for AI scale demand. How do we now use hydrogen for that solution that we require and to move that forward? In hydrogen use cases, it's already here. There's data pilots running in the Netherlands funded under the EU. Japan are using fuel cells in their telecom towers. It's a simple solution. Your fuel cell there, so if your grid does go down in an emergency or natural disaster, you still have communications. Where at the minute all of our towers are connected to the grid goes down, your mobile phone goes down. And we become used to the mobile phone, it's like your third arm. If you don't have IT coverage, you're out of communication. An interesting fact, and the newspaper I read a couple of weeks ago, when people look for hotels now, what's the number one choice, number one thing they want in an hotel? Any ideas? Cleanliness? Quality? Food? Speed of Wi-Fi. Not just Wi-Fi, speed of Wi-Fi. That's now the top demand in people's hotel choices. The food could be rubbish, the view could be rubbish, the bed could be made out of stone, but that doesn't think they want fast Wi-Fi. How many of you in this room over the last 6 months have lost coverage in your phone and you feel socially lost? lost, you're isolated. You're like Desert Island Dick or Robinson Crusoe. You're in the middle of Porto, but you've no signal. You might as well be on a digital desert island, because nobody can send you photographs of a cat meowing or something. But that's the world we live in. And that's where we've got to. And in order to facilitate that, we need to be thinking smarter and not thinking linear. If we look at California, Google are now using hydrogen. There's a young lady that, when you're trying to organize conferences, you do a lot of chasing, as you would know, right? And we were chasing a young girl from Google in America to come to speak at our conference. And it's about hydrogen for data centers. I got an email from her last night, she's going to come, but she's moved jobs. She's now the hydrogen lead for Amazon. That's not headlines, that's just simple. Amazon now have appointed a hydrogen lead. They're not doing it to get your parcels faster. They're doing it because they need to be greener and leaner and remove that social distaste that people have for data centers and Amazon. When people think of Amazon, they think of hard jobs, long service, sweatshops. So Amazon are looking to clean up their image. So they're doing it because it makes commercial sense. This lady now is the hydrogen lead for Amazon. And she'll be speaking in Dublin. And that's the way they are moving. So how do we start then looking at that, not just look at them as prototypes? Same as we said yesterday, how do you develop the technology here and export the technology and get better return? Google are now doing RBR clean energy tracking because it makes sense for them. They're tracking their energy use, they're reporting on their energy use, and they have their new image. But that Google uses the AI, who they control, to shift their computational tasks to places where renewables are abundant, or at times when renewables are abundant. So if it's daytime here, they do the computing somewhere where it's nighttime, the wind's blowing, less energy load, or vice versa. And that makes sense, because that gives a time-matched clean energy. We talked yesterday about sitting in Porto, doing your work, but you're working in Alaska. Those times you're here now, AI gives us that, the clean energy reinforces that. And it gives us that chance to where using hydrogen and other clean energy vectors, we now have a blueprint that you can follow. The one I talked earlier about, Leadfall. This is Norwegian. They're using the water from the fjord for cooling the data center. They're also using the energy from 100% hydropower. And this repurposed mine, so not all mines are bad. They've repurposed it now to be a data center, state-of-the-art data center, and it's slashing the PUE cost to 1.15. It's an example of using your natural geography to advantage. 100% hydropower was they had. The mine was cooled down, so they don't need external cooling, and they don't need that parasitic load of energy to cool the data center. Again, somebody thinking outside the box, watching your doorstep for an opportunity. We talked also then about, as we move to net zero, how we repurpose existing assets, how we use retrofitting here. It's costly, has long-term gains. What was built for yesterday is expensive to update, but it's not impossible. So as we look to that, hyperscalers can invest, but SMEs struggle because of the cost, the capital costs. Government grants in the US are helping them do this. EU's looking at it, and they're turning the investment puzzle. Retrofitting might cut our carbon costs, but it needs upfront capital. And when you go to a bank, they haven't got the economic equation to say, I'm saving carbon costs, so therefore that's an asset. Banks, finance institutions need to see your carbon footprint and reduction of your carbon footprint as an asset that has monetary value. And that last bit there is the challenge. If you go to a bank and say, right, I want to repurpose this building, you have a physical infrastructure, they'll loan you money against that. So the world of finance needs to shape, and it needs to have incentives so that we can accelerate the adoption of change. Our barrier and grid limits. We talked about the grid bottlenecks, Texas renewables curtailment. There's too much solar and not enough transmission at different times of the day. So there are fixes on-site storage and grid updates. So even when cheap renewables were available, the grid doesn't need them, so Microsoft is testing hydrogen. So in high growth zones, grid access, grid data need that regeneration, looking at microgrids and looking at hydrogen to bypass those bottlenecks. So as some projects are currently delayed or scrapped because the local grid can't handle them, where do you think those projects are going? At least 6 projects looking at Ireland last year, because of the grid bottleneck, went to Norway, Sweden and Austria. Investment is mobile, investment has a time frame. If Porto or Ireland can't facilitate investment, they will look elsewhere. And that's that change that we need to look at. We talked about it, and how we use hydrogen to overcome that. So if I ask you a question, now you're not allowed to go to sleep. You have 5 up there. What's the biggest barrier in your head to green data? What's holding us back? Is it cost, technology readiness, regulation, awareness, or grid access? Hands up for cost. You have a look online, so who's putting a hand up. Nobody for cost. Technology readiness. Ah, come on, folks. Somebody has to be awake. Your eyes are open. Regulation. There we go. Now we're getting there. Awareness. And grid access. I think grid access comes in second, but in my head, that's what's holding us back, that biggest barrier. But not in the fashion we think. We should be using grid access as an argument for bringing hydrogen in, to create the technology headroom, and to think about what we're doing. But all of them are barriers, without a shadow of doubt, and all of them are barriers in different parts of the world. Because geopolitical tension and opportunity there creates that. And there will be other barriers coming up and down, such as, if you look at any investment, any company that's investing anywhere, the first thing they look for is government stability and legislation stability. That's why countries like Porto and Ireland and other countries, foreign direct investment, look to here, because it's a stable country. Stable government, stable rules. But you have a stable grid. It's now getting to where the two are nearly as important. And the return on investment is based on that and predicated on that. So if we look to a solutions roadmap where we go from prototype to paradigm, how do we optimize workloads? How do we get 100% CFE hourly? Advanced cooling, and by 2050 look at AI self-healing grids. Our timeline, in my head, you have your pilots already. We can then grow to scale by using AI and the tools that the pilots provide, so it becomes self-reinforcing. By 2040, we'll have hybrid clean hydrogen valleys, and by 2050, full autonomy in those closed-loop systems. And that will happen. That's growing. It's that twin growth, clean energy and digital, that's going to move Europe forward to remain competitive in an international market that's challenging. I was talking to one of the group here over lunch. My new best friend's Donald Trump. Not because I like him, because I like what he's doing, because what he's doing creates an opportunity for us. And never waste a good crisis. And it's true, when he got elected, can I remember one of the first quotes he came out with, and he actually used it again the other day. What was the first quote he tweeted when he was elected, after he was elected? Drill, baby, drill. It's music to my ears. Because as long as they're focused on that, it leaves space for us to focus elsewhere. And for too long, we've always looked west for solutions. We need to look south and east. The Inflation Reduction Act was one of the best things that the previous government had planned. He stopped it completely. Now, don't get it wrong. One of the ladies in the government Energy Act that was speaking for us 1 week said yes, he's speaking, and 2 weeks later she lost her job. That's how volatile the environment is there, never mind the grid. So it's not a good place to be, but the more he creates like that, it creates opportunity. We look at the north coast of Africa across as a solar powerhouse for the energy for Europe. Look at your proximity to that technology, that opportunity, that geography. Look at your solar here and how your energy provides domestic but also international opportunity. And look at that with the Americans used to call it a moonshot. It's a staircase. Your steps are there. You've planned it. They're not massive steps. They're taking incremental steps. And they're now looking from pilots to scale valleys to be fully autonomous off-grid. And that's about crawling, walking, running. So a call to action. Where do you see yourselves each having a role in the valley? Who needs to step up in your work and what you're doing? In the technical end, start measuring your carbon per query. Not per question, per query on your phones. And then look at how we mandate transparency. How do we bring a new narrative to discussions, to your research, to your papers? I was impressed with some of the papers out along the window there. During lunchtime, up and down. Fantastic work. So you have a knowledge capital here. You don't need me to tell you that. So how do you then take that to mandate a transparency? It provides the openness, it provides the opportunity. And as one of the participants said yesterday, his country has all of those rules, but they don't have the money. Europe has the money. Europe has a need, and Europe would pay to meet that need. In EU funds, you have the hydrogen calls, you have the fuel cell, the Clean Hydrogen Partnership. Their calls come out every quarter, but there are bigger calls where there's transnational opportunity and national opportunity projects. And one of the things that we're doing in Hydrogen Ireland is engaging with our MEPs to get them to step up to the plate. Do the job properly, and engage at a higher level. So the voice of Ireland is heard on a better scale, and probably the voice of Portugal. Because given the renewable assets that you have and we have, we're not on the periphery of Europe, we're at the center of Europe. Geographically, we're at the edge. But technically and in energy scales, we're at the center. And how do you then use that message and carry that message forward? How do we then develop a converged clean future where it's not data and or energy? The two are converging to a shared future. How do we use data valleys as engines of sustainability? If we build them right, the last line, data doesn't have to cost us the earth. Data can help save the earth because it's given transparency to their carbon footprint, their carbon costs, and the damage that's been caused, and then how do we move that forward? On your slides, you'll have that to have a look at. And the last one is, my thoughts are where data valleys are emergent ecosystems, where digital infrastructure meets renewable innovation, green data centers, hydrogen renewable powered, AI-intensive industries then become an inward investor of choice for the quality jobs we talked about and the spin-off of that. So we decouple digital growth from the current measurement of carbon emissions, and we co-locate power with low carbon energy and cooling systems. We then have the potential to evolve into a climate positive innovation zones. We become that digital infrastructure, that digital valley. We export not just the data services, but the surplus energy. And importantly, a lot of things that I should have mentioned, I forgot. You get paid not just for your clean energy, but you get paid for the carbon you're saving. So for your revenue stream, you have two revenues in it. Your green energy and your carbon costs. And currently airlines are paying for carbon offsetting. So you have a dual revenue stream. And then we look at where Valley and AI are not just trained on zero computing, they're cooled by seawater or lakes, they're powered by hydrogen microgrids, all the way in supporting local economies and biodiversity. Folks, thank you very much for your time. I hope it was as
Thank
good
you,
as
Paul.
yesterday. Your first name, please, and then your question. I think, look, back here.
I'm sorry.
Hello, thanks for the presentation. My name is Miguel. You talked about the Norway fjords. I'm sorry, I'm not very aware of what it is, but isn't it using something, for example, typical to Norway, that it's something very cold?
Seawater.
To cool down the data center?
They're
Can't
using
it have
They're
that
using the
also?
water from the sea, bringing it in
Mm.
to cool the thing, and then putting it back out.
Oh, okay.
So it's using the natural assets they have. They've located the data center in a mine, so the ambient temperature in the mine is lower than the outside temperature, but it's stable. If we look at data centers, say a data center in Portugal, you could have 20 degrees fluctuation in temperature over the year. But in a mine, you've no fluctuation. You think of how the stable temperature can be used to offset your heating and cooling costs for different industries. And data centers, unlike coal miners, don't mind being down a mine. But so they've been innovative. They've looked to where their local geography lends itself towards that opportunity. No different to hydropower years ago, where people look at local geography, how to harness the power of rivers and that, and different renewables. What's the fluctuation in the temperature of the sea here? 6, 7 degrees? No, how can you use that? That's a tight control. How do you use that then for something else? If you look at all the different coal mines throughout the world that are now not being used, how could they be repurposed? So, what was the dirty industry, they're closed and there's massive job losses. How do you repurpose that infrastructure to create job opportunities in a clean industry?
Okay, thank you.
Hello, thank you for the presentation. My name is Gabriela. I have a question regarding the barrier with the grid limits. I still don't understand why it's a barrier, because if you're using the centralized approach for the grid, okay, it's understandable. But if you're using the decentralized approach, that shouldn't be a problem.
It's not decentralized, isn't a problem, but at the minute grids are not decentralized. In Ireland, the most of our renewables are on the west coast, and the most of our demand is on the east coast. So as they bring that renewables across at different times, it's not needed, so they curtail it. So one of the solutions that one of the companies in Hydrogen Ireland is looking at is co-located electrolyzers along the points of what I call the points of pain, where the grid can go no further because it's not needed here. So rather than curtailing it and wasting it and losing it, capture it as hydrogen, store it, and use it for grid offsetting.
Okay, it's more
Again,
a location problem then.
Again, it's looking at geography, looking where the sweet point is and how you locate there.
Okay, thank you.
I will take from the audience online. The first one, in the last update from the IEA at the global conference on energy efficiency, it was noted that the highest energy use now comes from air conditioners, which is higher than the data centers' energy consumption. What is your reflection on that?
I'm old enough to remember we had no air conditioning. And in Ireland, that was no problem. Now we've become used to it, same as the mobile phones. We've become creatures of comfort. Those of you in the room, your parents would have grown up, there's no such thing as air conditioning. We all survived. But we've become used to it, so therefore we have to accommodate it. And we need to find smarter ways of air conditioning rather than just on and off. It has to be about energy efficiency. It has to be what was talked about yesterday, smarter buildings, and using AI to control that energy.
And optimize. Yeah.
We have the mechanism to control it rather than just a physical on-off switch. Or as people do in hotel rooms, when they're going out, turn it down to 18, leave the electric on and go away for the day. So that the room's cool when they come back that night. We need, our biggest change is change of habit. and recognizing that the first step in any journey towards net zero is efficiencies. Where can we find efficiencies, that low-hanging fruit that is there to create greater system resource efficiency?
Okay, thanks. Another one from here, and then we will see if you have more. Thanks for your engaging and interesting presentation and for bringing this subject up and presenting a potential solution. It's important to create awareness and have a conversation about it. I'd like to know your thoughts on biological computer chips and their potential impact on Pillar 3.
Biological computer chips. If I'm honest, not a clue. And that's been honest, because it's not my area of expertise. But it's going in the right direction. And it's been smarter, it's been wiser to look at what we talked about, Pillar 3, that hardware efficiency. It doesn't have to be a large, power-hungry chip that was designed 30 years ago, still being used today. The advances that have been made continue to accelerate. How do we harness that? How do we capture that? And the biological, one of the things that we've also worked in is biorefineries and the energy from that and biopackaging. So nature has a lot of answers.
Yeah.
Sorry, nature has a lot of solutions that we need to find answers for.
Yeah.
And that last point, data doesn't have to cost the earth.
Yeah. Any more questions? No? Okay.
Interestingly, when we talked to the Clean Hydrogen Partnership about this year, they're not at the stage to fund data valleys. And that's part of the problem, because EU funding, people lobby for it, and 2 or 3 years later, the funding comes out what the big companies want. The steel industry, the coal industry, all of the hydrogen funding that's currently out now are looking for solutions for that. So even the mechanism for EU funding isn't agile enough. But if you look at the data challenge now and the speed of the data challenge, look to that agility for speeding up. We talked yesterday about how we use blockchain for following the track of green electrons to green molecules in a mixed-use electrolyzer. The technology's there. It's how we apply it, how we use it in a smart fashion.
Okay. Thanks a lot again.
Again, slides, we circulate on the paper. Thank you very much indeed.
Thank you. Okay, moving on. It's your turn, Paulo. Okay. 7. A apresentação já lá está. Okay.
Hello, good afternoon.
Okay, I will.
Okay.
Just a short presentation. I have your bio, but I know him by heart. So I have the great pleasure of receiving here my colleague and friend Paulo Brito. He's from Instituto IPP, Politecnico de Porto Alegre. He is always a partner of AIRE project. You remember, Renar presented yesterday. And so we are keen to hear your presentation. So the floor is yours.
Okay, thank you very much. Good afternoon, everybody. First of all, I would like to thank the invitation to be here. It's a pleasure. It's an honor to be here in this summer school related to hydrogen and fuel cells technologies. My name is Paulo Brito. In fact, thank you for the presentation. I'm from the Porto Alegre Polytechnic University. In English, you can say in this way. In Portuguese, it's Polytechnic Institute. But my talk, it's about different ways of production of hydrogen and renewable gases from waste materials. First, I would like to present a little bit my research center. We have a research center which is called Valoriza. And this Valoriza comes from valorization of endogenous resources, work mainly in the 2 or 3 areas. One is circular economy, then related, one of them more related to waste materials and waste valorization, and another field of research is related to sustainable production and environment. So in this waste valorization, we have been working for some time in technologies that can convert waste materials in renewable gases, methane, hydrogen, syngas, and so on. So we have been working mainly in the developing technologies. We are our position in terms of research is to research at high levels of TRL. So we have an industrial lab that we with different pilot units that use different types of technologies like thermochemical technologies, biochemical, electrochemical technologies in order to convert waste materials, convert them in something that has value, in particular renewable gases. In terms of formation, we have 2 specific formations that are connected with this summer school. We have a master in energy recovery technologies and energy production, and also we have a new PhD degree. It's a new one. It's related to hydrogen and renewable gases. I think it's the only one PhD in Portugal, at least in Portugal, that is focused on hydrogen and renewable gases. So my talk, I will do a brief introduction in relation to thermochemical technologies. My focus today, it will be gasification, thermochemical gasification, since the main point it's how can we produce renewable gases, and in particular hydrogen. And then if I have time, I don't know, I will give some, I will show some of our projects that we are running, mainly European projects that are connected and related to this subject. So all our work, it's very connected. Probably you have already seen and talk about European Green Deal. So in fact, all our research in Valoriza, it's connected with these objectives, these climate neutrality by 2050. We know that these objectives, sometimes there are some people, some countries that are looking to these objectives and say that probably it's not the best way. We continue to think that we should continue the way in this direction to have a climate neutrality, because we need to change our it's important not to continue changing in this way our environment. And we also all know that we are using too much resources. We are producing a lot of wastes, and part of wastes that we are producing, they are no useful. So they go to landfill, and so we need to increment the circular economy and try to valorize all the wastes that for the moment there are no application, not valorization. So one of the points, it's the production of biomethane, biogas and biomethane. As you know, or probably you don't know all, but in Europe it's an objective, a big objective in terms of production of biomethane, since biomethane is it's the same molecule that natural gas. So in this way, the most important or the most important technology to produce biomethane, it's an aerobic digestion. It's about biological processes. Can be can use a lots of different waste materials, but usually we use this technology when the amount of water, the humidity of the wastes are very high. So this is one way. The Repower EU, which is also a very important program in Europe after the starting of the war between Russia and Ukraine, gives some big objectives in relation to biomethane. The idea is to increase the production of biomethane 10 times. So this is a very big objective. Portugal, for example, since we don't have lots of biomethane production, it's not very difficult to increase 10 times. But in fact, there are lots of projects starting in Portugal, which is good in terms of biomethane production. In relation to hydrogen, during this summer school, you probably, or you are listing different ways of using and producing hydrogen. In this particular talk, we want to go to different types of primary energy sources. So we know that we can use hydrogen to store renewable sources of energy. Yeah, I think it's the more novel application for now. It's to store this type of energy in a chemical way. But as you know, hydrogen is used, we use hydrogen for lots of things. Probably most of the materials that we have here in this room use hydrogen in the production process, like polymers, like all types of materials. So hydrogen, it's not only for a fuel that is used as a fuel, but is also a very important chemical in all industry. And so it's possible to decarbonize the industry with hydrogen. So in our case and in our research, the idea is to use specifically the biomass and biomass materials and organic materials that can be converted in hydrogen with similar process that we are now using to the production of hydrogen from natural gas or from oil. So the idea now the production of hydrogen comes mainly from steam reforming, like a process like this. It's a high temperature process. Can also, this process, the steam reforming, has a process that we can also increase the amount of hydrogen using a water-gas shift reaction, which is in fact a reaction that uses steam, and we can increase the amount of hydrogen that is in the gas stream. So the idea is to work very close to this process. So we are looking not for oil or natural gas as a feedstock to the production of hydrogen. So we are looking for biomass materials, organic materials, and using this type of thermochemical processes. Very quickly, the thermochemical processes we can divide it in 3 or 4 main process. We have in the one part the combustion of material. It's the incineration process. We only obtain heat. It's the final product. It's heat, it's energy, thermal energy. In the other part of the process, we have the pyrolysis process. In this case, we don't use any oxidant, so any oxygen. It's a pure thermal processes that break the chemical bonds between atoms in the molecules and then convert the biomass materials in the more simple compounds. In the pyrolysis, we obtain a solid part, which is a biochar. It depends on the the conditions of the process, but we can obtain a biochar, we can obtain also bio oil, and also a syngas from this process. But in the middle of these two processes, we have the gasification. In the combustion, we give all the oxygen to have a complete oxidation of the organic material. In pyrolysis, we use only the thermal break of the organic material. In the middle, it's gasification. We use a small part of oxygen, the stoichiometric oxygen, around 20–30% of the stoichiometric oxygen, which give me some thermal energy. So it's possible to develop some exothermical reactions that give me energy to break all the chemical bonds in the material. So the main product of this process, thermochemical process, is a gas, a syngas, which is very rich in hydrogen, which is very rich in CO, and also it's very rich in the CH4. Well, this is a table. Then in the end, I will give the presentation for you. This is a table that is a summary of the principal thermochemical processes that can be used to the production of hydrogen. If you see in this table, I don't know if I can point. No. But in this table, gasification, in fact, it's probably the most important process, thermochemical process, if we want to obtain renewable gases like hydrogen or methane. If we look now specifically to thermal gasification, we can say they're very simple and to understand. Then we start with some feedstocks. Feedstocks are materials, mainly organic materials, of course. Then with this feedstock, it's possible to convert them in a syngas, which is rich, as I said, in hydrogen and carbon monoxide. And then we can make an upgrading of the gas. We need to clean, as I will show you later. But this is a syngas, which means that we can use this gas to produce lots of different compounds. What are the main feedstocks that we can use? For example, and very relevant to Portugal, it's forest wastes. As you know, we always have problems inside country because of the summer fires all over the region, territory of Portugal. Probably the forests are not clean. If we can clean the forest and use the biomass, it's very interesting to convert them in hydrogen and renewable gases with this type of technologies. But we have also agriculture wastes. These are some numbers also from Portugal. There are lots of wastes that we produce in agriculture and that are not useful. We know that in terms of agriculture waste, some of them are used to feed animals, for example. Other wastes are very useful to the soil because our soils are poor with low carbon. So it's possible to use the agriculture wastes to increase the carbon of the soils. It's true, but there are lots of agriculture wastes, and that can be. There is no utility at this moment that can be also converted, and the amount of these wastes are very big, and it's possible to attend, for example, around 20% of our needs in terms of fuels. So it's a very important name. Another feedstock, it's the municipal solid waste. More or less half of our municipal solid wastes goes to the landfill with any particular application, even production of biogas. Most of our landfills, they are not producing any particular biogas. So if we look to this amount of wastes that we put in the landfill, and part of them are in fact organic wastes, there is a very big amount that can be, with this type of technologies, converted to hydrogen and converted to renewable gases. Some of our projects are in this particular field. So when we convert these materials in a syngas, then we can have lots of different possibilities in terms of production of new chemicals, new materials. We can go and have methanol to produce methanol with syngas. We can produce with CO2 and hydrogen, or CO and hydrogen. As you know, methanol, it's very important. We are looking for methanol to be a fuel for maritime transportation. So this is a route that we can use to produce methanol from syngas. But if you go to Fischer-Tropsch synthesis, it's possible to produce gasolines, jet to aviation, to SAF, to aviation, and so on, and lots of chemicals and polymers and so on. So this is the route for using of wastes to different products. Now, gasification, it's in the maturity of TRL around 7. What does this means? This means that we have lots of demonstration projects running all over the world, and in particular in Europe. We know very well gasification because we are doing gasification for more than 200 years with coke and gasification of coke and so on. But in fact, why this is so low, the TRL of waste? Because this is a different material. In coke, it's carbon, and in this case, biomass. We have carbon, oxygen, hydrogen, and so on. So this is the point why gasification, it's not with more high TRL. So very quickly, this is the gasification process. We can, as I said, we need to input some oxidant. We usually use oxygen, not the stoichiometric oxygen, but also a small part, around 20–25% of the stoichiometric oxygen. If we use the oxygen that are in air, we have 79% of nitrogen in air, so all of this nitrogen goes inside our systems, and the gas that the syngas, it's a poor syngas because around 50% of the syngas is nitrogen. So what can we do? We can use, for example, with pure oxygen. It's not, this is a very interesting way, because as you, in this summer school, you are probably, you have heard about lots about electrolyzers, the production of hydrogen with electrolyzers, and in electrolyzer we produce hydrogen and oxygen. So if you can combine these two types of approach, one using renewable electricity and close to another one that wants to valorize this type of waste materials, then we can use the oxygen that we are producing in electrolyzers directly in the gasification process. If we want to increase the amount of hydrogen in the gas, so another possibility is to use steam, as you see in the picture. So if you use steam, the water-gas shift reaction that I showed before can be incremented, and the amount of hydrogen it's higher. Very quickly, what we need to do with materials. So it's important to have a pretreatment. It's important to have a reduction in terms of alkali metals in the process, since we are working in thermochemical processes at high temperature. So some alkali metals are not good in the process because they can form clickers and so on. The chloride, another important element that it's very can destroy and have corrosion problems in the high temperature process. So it's important sometimes to have water washing of the materials. Then it's important to drying, because these technologies usually at high temperature used dry materials. In fact, now we are also working in the hydrogasifications. So this is process that run at high temperature, but also at high pressure. It's possible in this case to work with feedstock with high humidity. Then sometimes it's important to have a size reduction. We can also need to densify the material in terms of doing pellets in order to have materials with good uniformity to have a good and controlled process. What are the main, one of the main issues of the gasification? Probably this is probably the most important problem, because the biomass has a lots of compounds, cyclic compounds like benzene, toluene, and so on, that at the temperature that we run the gasification, which is around 80, 100 degrees, 90, 100 degrees, this type of compounds does not convert. So it's very difficult to convert this type of compounds, and at this temperature. So the syngas has a lots of this type of compounds, and it's a problem in all of the operation after the gasification process, because as you know, tars, they stick to the surface and have problems with equipment. So what are the strategies to overcome this problem? One of the strategies is to using catalysts inside the reactor that can help in the conversion of this type of compounds. We work with fluidized bed reactors that we can put there dolomite, which is calcium magnesium carbonate, that is a catalyst to convert this type of compounds and minimize the tar formation in the reactor. So this is different types of gasifiers. I have said about fluidized bed reactors, but now it is very interesting in terms of research about plasma reactors. They are so far very expensive because we have to produce the plasma. But in this case, with the plasma, it's usually the quality of the syngas is very high. The amounts of tars and all these compounds, contaminations, are very low. But plasma, now it's not, we have some reactors that are in the market, but it's so far very expensive technologies. One of the most technologies that are running in the field are this type of technology, which is a downdraft reactor. And here you can see a typical composition of the syngas that is produced from this reactor. We have around 50 to 20% of hydrogen in the gas. If we want to increase the amount of hydrogen, for example, we can use a dual fluidized bed reactor. In the dual fluidized bed reactor, we have one chamber that we promote the combustion reaction with the 20% of oxygen that I said before. And then in another chamber, we produce the gasification process, so the conversion. In this case, this is more or less representation of this type of approach. And in this case, the gas composition, it's the hydrogen in the gas, it increases. So in this case, we are now talking about 35 to 45% of hydrogen in the gas. I have more. 5 minutes? Okay. In terms of another possibility, it's to use sorption-enhanced reforming. It's a carrier, in this case is carbon oxide, that go inside the gasification and take out the CO2 in the form of calcium carbonate. In this case, if we use this approach in gasification, the amount of hydrogen that we are going to obtain in the gas goes to around 7% of hydrogen. So we are increasing the amount of hydrogen. Then we can take this gas, this syngas, with around 17% of hydrogen, and then we can also increase the amount of hydrogen by doing in the separated reactor a water-gas shift reaction. And then, after this, we have a gas with a very high concentration of hydrogen. We need to clean this gas because we have sulfur compounds. Usually in the biomass, they are sulfur, so we need to clean the gas in terms of sulfur compounds, nitrogen elimination, and so on. And after this clean process, and also TARS, after this clean, I don't have time to explain in more detail the tar removal, but we can use scrubbers with the different type of organic compounds. We can also have scrubbers to remove CO2 from the gas. Then, in the last stage, we have a high concentration of a gas in terms of hydrogen, but then we can make the final separation in order to obtain, we can obtain, if you want, 99.999% of pure hydrogen in the gas. But in this case, we need to use some separation process like with the filters, with membranes that allowed us to produce a very pure hydrogen. So this is the process, the general process, in order to obtain hydrogen that can be used in the industry, can be used in mobility, in fuel cells, can be used in different applications, like those that are in this slide. So very quickly, these are some results that we obtained with different feedstocks. From this is in gasification process with forest residues, coffees, vine prunings, all of feedstocks that we have a lot in Porto Alegre in our region. And then, if Professor Alexandre give me more 2 minutes, 1 minute, some demonstration projects. This is iFuel Up. iFuel Up, it's a European project. with some Portuguese Portuguese institutions. The leader of this project is BioRef. It's a collaborative laboratory. And the idea of this project is to using gasification, not to produce hydrogen as a final product, but to produce methane with a methanation reaction. So we produce, we take feedstock, forest, and sludge from different type of wastewater treatment plants. Then we convert them in a syngas, and then we convert the syngas with a methanation reaction in methane that is used for transportation. We are doing a demonstration unit in Tondela, here in Portugal, and this is a very important project in this, using gasification, not to produce hydrogen, but to produce methane. This is another European project. In this case, we are the coordinators. It's Pyrograph, which use thermochemical processes, pyrolysis, with the help of solar-assisted concentrators. So the idea is to combine the thermochemical process and use part of the energy to the process by solar concentration process. Idea here is also to produce different materials like carbon, bio-oil, biochar, and also a gas which is very rich in nitrogen. I have to close, I know. Resist, it's also international project. In this case, the idea is to build a biorefinery that can produce hydrogen to mobility, and using the waste materials that we can obtain in the forest near the village, small village that have agriculture, they have forestry, and then they collect all the biomass that in order to clean the area around the village, and then in a centralized unit that we are built in Porto Alegre, we are doing a biorefinery in order to produce renewable gas, but with a focus on hydrogen that can be used in the region. Okay, that's it. It's a valley region.
Thank you very much, Paulo. Okay. I will start with these two quick questions we have here. First one, can you explain why Alentejo is the main producer of municipal waste, and considering that it is in the interior of Portugal and with less focus by the government, is that an opportunity or a challenge?
Yeah, because Alentejo, it's a very, very big region. With we don't have a lots of people, in fact, but it's a very, very big region. And I think it's both. It's a challenge because, as I said, there are a very big part of this waste, municipal waste, there are going to landfill. So this is a challenge. Why we don't use that waste in terms of valorization? But also it's important that we look and have solutions to that type of feedstocks.
Thanks. The second one is what is done to the byproducts, for example, tar?
In our case, the tars that we produce in the process. In fact, what we are studying, it's not to have tars as a final product, it's to convert to recycling the tars, then they go again inside the reactor, and then we increase the time of residence inside the reactor, and we try to, but in a linear way, the tars could have very different applications. It's possible to also to valorize the tars because there are some compounds that are useful for the
example,
different
for roads and
in this case,
They are
yeah,
many
could be
impurities.
also used in
Yeah.
in this type of roads and materials. Yes.
Thanks. And now here, Gabriela.
Thank you for the presentation. I just want to know if there is a competitive market about the forest waste. For example, they can also be used for, or the forest waste also can be used for pellets. So do you have there any kind of problems?
Yes and no. Yes, there is a. In our case, there is no competition because most of the pellets that they are producing are from timber, not from the wastes, in fact. Because when they are using wastes, they are usually, they could have problems in terms of the quality of the feedstock. Because if they want to produce a pellet with a different, with a high quality, they should use, usually they use only the timber and in the tree. So in our case, we are looking for wastes that are producing in the forest, okay? But I thought your question is in the direction, for example, like some of these forest materials could be very useful to the forest because the soil are very poor. But in the gasification, one of the main product is the gas, okay, the syngas. But we also produce a biochar, and this biochar we have also different projects that using the biochar in the soils for agriculture, for forest, and so on. So yes, we can compete for this, but in fact we are trying to use different materials that from production of pellets.
Thank you.
Thank you. No more questions? Then we have to close because we have still another presentation. So thank you very much,
Okay.
Paulo.
Thank you very much for the invitation.
Okay. You want? Perhaps at the end of the next one. The table. Yeah. Okay. In the break. Okay. Okay, Duncan is here. Hello. So I have the pleasure of presenting our next, hi Duncan, our next speaker. It is with a great pleasure that we receive Duncan Otterson. He's in fact the chief designer engineer of the Rolls-Royce Hydrogen Demonstrated Program, and he will present his talk is on hydrogen direct burn combustion, route to gas turbine ground test demonstration. So you have the floor, Duncan, and thank you very much.
Thank you very much for inviting me. Can I just check? Can everyone hear me okay? Is it okay?
It's okay.
Yeah, good. So yeah, good afternoon, everyone. Yes, I'm phoning from Derby in the UK, where I'm a chief design engineer for the Hydrogen Demonstrator Program. Basically, I work for the Civil Aerospace Division. Rolls-Royce as a whole integrates complex power systems for safety critical applications in land and air and sea applications. And I work in the Civil Aerospace Division in Derby. And I work in the research and technology area, where we mature technologies ready for market applications of the future. So some of the work we've been doing is supporting, as you can see from this foil here, our journey to net zero carbon. We fully support the route to a net zero position in aviation propulsion and aviation as a whole, recognizing that sort of currently aviation is about 2.4% of the carbon emissions in the world. So what we've been working on is, as in Rolls-Royce, is a sort of a strategy of, as you can see from this chart, our route to net zero is a route to minimize the fuel we burn in our existing fleets, which is a question of improving the efficiency of our gas turbines, which have over the last several decades reduced significantly in the amount of fuel they burn. And we do that in two ways, by sort of introducing efficiency measures on our current fleets, but also step changes in our products. And note the second column is the UltraFan concept, which we're currently maturing here in Derby. It offers a significant fuel efficiency increase. On the third column there, you can see that we're also engaged in looking at SAF, which is sustainable aviation fuel, so hence fuels derived from largely renewable sources such as biomass. And our engines are compatible with that, and future engines will be as well. So as soon as the market shifts towards that kind of fuel, we'll be ready with equipment that will support that. But beyond that, we're also looking, obviously, to totally remove carbon from the propulsion system, and that's the areas of more electric and electric propulsion. But the cryogenic and hydrogen cryogenics are one route towards that. So that's something that we've been working on. And the presentation I'm going to give today describes an overview of the work we're doing this year to achieve a ground test demonstration on one of our business aviation products. So I'm hoping to give you an idea of the challenges we face, the progress we've made so far, and the progress that we need to make in the future to make some of these, the use of hydrogen in aviation more of a reality. So if you could go to the next slide, please. So again, another context setter, but for those of you that curious as to where we think hydrogen can be applied in aviation by 2050. This chart is really just to summarize that. So you can see the columns indicate on the top left is urban air mobility of say 4 to 6 people, commuter aircraft of say 6 to 10, 15 people, regional aircraft of maybe 30 to 40 to 70 people. And then narrow body and small and medium biz jets is really the sort of 737, 320 size, A320 size aircraft. And the wide body are obviously the large international aircraft such as 787 or A350. And we, in 2050, we think at Rolls-Royce that basically, as you can see from the middle, the gas turbine will continue to dominate aircraft propulsion. So that, in the previous files I was showing, the accelerated development of the gas turbines essential to protect our route to net zero. But you can see on the bottom 2 or 3 rows that we see hydrogen being used in fuel cells, with a gas turbine with a fuel cell, and in a combusting gas turbine in the period, again, depending on the alignment of market need and so on. So our job this year is to try and explore the technology around that sector of the market. So the engine size we're looking at could well be appropriate in the regional narrow body space. I'm afraid I can't see any questions, so I'm going to keep going and then perhaps take questions at the end if that's okay. So if you go to the next slide, please. So what do we see as the key questions about using hydrogen in aerospace? Well, I mean, I outlined them here, but they're really clustered around sort of 3 areas of technology, policy, and regulation. And I think this presentation will focus obviously on some of the technology acquisition we're undergoing now. But I'd also draw your attention to the need for regulation. Aviation's a highly regulated industry. We do have to meet standards rigorously and show that we meet those standards. And developing those standards is important when using new fuels, and making sure that they're well understood across the industry, and that we can access a supply chain that understands those standards, and that we are, delivering products that can demonstrate to meet those standards. So really, the question is, can an aircraft be designed with acceptable range and competitive economics? And that's the key question. Rolls-Royce doesn't design aircraft. We supply complex systems to integrators who supply the aircraft, and their choices and the optimization of the aircraft level will influence the sort of power system solutions. That delivers a load of technology challenges, and the question is, can they be overcome, and can they be and the products that derives from them can be certified at today's level of safety for an economic cost. And there are some non-CO2 impacts of introducing hydrogen. There are changes in the emissions that you expect from a turbine. There'll be other changes without doubt, and those negative impacts, can they be overcome, is an important thing to understand. For the fifth point is, and it's important to recognise that with all these technologies, we exist in an ecosystem of supply of hydrogen, and this only makes sense as a net zero reduction if the hydrogen we receive is in effect green. And so is that going to be available for the aviation market at an economically viable price is a strong question around the introduction of hydrogen in aerospace. And then obviously those, I'm sure most people have been flying, but you will be aware of the immense and intricate infrastructure of airports and the supply chains that keep commercial aerospace, commercial aviation going. That will require a vast amount of investment in the time frame. So these need to be in place before we can convert to hydrogen in commuter and regional and small and medium range aircraft. And can we do that in the 2050 timeframe? That's a really interesting question, and the rate at which we progress will be determined by probably by technology acquisition and policy. Okay, the next question, please. So Rolls-Royce is sort of illustrating the challenges. It's clearly supplying the hydrogen to the airport and make it available as aeroplanes need it. It's storing it, and you can see there that we think cryogenic storage and liquid hydrogen is probably important and possible both on the ground and on the aircraft. And what I really want to show on the last three columns is the things that Rolls-Royce gets heavily involved in. As we supply engines, we will be looking at managing the liquid hydrogen, pumping it. We'll be looking at converting it into gas, and then we'll be looking at metering and combusting it. And this presentation really zeroing in on the last column, the gaseous metering and combustion. We'll show you how we're going to demonstrate that this year. Okay, next. So I'm an engineer. My background is mechanical design engineer. I've been a chartered engineer for over 25 years. So this isn't about science. It's about taking what you see on the left there, the high-level view, and making it a reality. And on the right, you can see columns which show some of our products, a couple of our products. The top one's a large engine, and the bottom one is one of the earlier prototypes of our hydrogen program. And you can see that is a complex mesh of harnesses, pipes, units around a gas turbine. And for scale, that engine is probably 2.5 meters long and about 1 meter in diameter. It's very easy. It's quite easy to draw the schematic on the left. You can see we get gaseous hydrogen, we interact with the baseline turbine systems, and we exchange heat and power with the airflow. We then meter it with the control system, and then we combust it. So that's what we've got to go and demonstrate in 2025. Go to the next slide. So we don't do this alone. It's quite expensive to develop one-off new products for engine test demonstration, and we rely on the support of universities and our university technology center network. And this chart really is just to give you an idea of what we're bringing together. The program that's supporting this ground test is the Cavendish activity. You can see in the last 3 columns that's funded by the Clean Aviation project out of the EU, as well as the ATI in the UK. And you can see feeding into that on the columns to the left of that are some funding from Germany into early stage combustion fundamentals, and some work in the UK around supplying the units and hardware and systems that would go into the Cavendish work. And then the output from our work goes into concept work, looking at how that would be applied in the future. So you can see that the Heaven program there converts our work into how we would fit this system into the UltraFan. And in the top right, you can see the range of funding agencies. And I draw your attention to the interest which EasyJet is providing to our work, and acknowledge their sort of contribution to the achievement of this program. Next slide, please. So what are we doing? Well, one of the things we're also trying to do on this program is to move quickly and learn fast. And so we're taking a sort of minimal viable product approach. Of these columns, we've done 2 of them. So in 2022, we took a donor engine, an A2100 engine, which is the sort of turboprop that is used on Hercules aircraft. It's also used on the Saab 2000. And we ran that on hydrogen gas in on a airfield in the UK, Boscombe Down, and showed that we could start and hold that at idle well. But where the credibility of the use of hydrogen really rests on it being applied to the sort of product that we can supply. So we then took the step to modify a Pearl 15 engine, which is a business aviation engine from the BR700 series of engines, which is an existing and certified product. And we've taken the step to modify that fuel system so that it can burn hydrogen. On the way, though, that product and all our gas turbine products uses the kerosene fuel for a couple of other functions as we deliver it to the combustor, and that is heat management. So it's a place to sink the heat from the engine, but also to actuate some of the control systems. So if we're going to use hydrogen as a fuel, we need to find other means of achieving that engine control and engine heat management without relying on kerosene. And that's what Engine Zero in the middle there does. And so we've proven via a test on our German site near Berlin, called Rolls-Royce site near Berlin, called Dahlewitz. We test that indoors in Germany, and have shown that we can find alternative means of managing the engine heat and the engine actuation, control actuation. So what we're focused on now is doing an outdoor test on an engine in Stennis in Louisiana in the USA. It's in a NASA site, and the benefit there is they have a lot of hydrogen because they test rocket engines there. So some of the fundamental problems about supplying enough hydrogen to run a gas turbine are removed, and we're working in a site which has a lot of experience of experimental testing with hydrogen. So we're trying to focus on that and achieve an engine test this year. Okay, so next one. So what have we done so far? Well, we talked about Boscombe Down. There's a lot of combustion testing going on, and that's finished. And we've shown that we can largely burn hydrogen very well in an existing combustor. There's more optimization we can do, but we've shown that we've got stable flame and stable control within the combustor, which is a good move. We talked about Engine Zero testing, and we're really continuing to work on our combustion testing, and we've done lots of work at lower temperatures in some of our pumping products. But you can see there's a bundle of work that we're doing and have done over the last few years as a result of our program. Now preparing the next steps. Okay, the next slide, please. So what are the challenges of burning gaseous hydrogen in a gas turbine? So I'm sure you're aware that gas turbine systems exist in industrial applications, but they're largely land-based, and we haven't really challenged how we would fit hydrogen and turbo machinery together in an aircraft with modern engines. There has been some work accessible in the literature on military prototypes in the 50s and 60s, but we haven't really done it with a modern engine. So this is where we're using the Pearl 15 to explore how that will be applied on modern products. So if we're going to take a modern product and put it on an aircraft, there's several things we need to do, and I call them technical program, and at the bottom there, the thinking about standards and regulations. So technically, we need to update the heat management system. So we will have to look at integrating different heat sources, different heat exchangers, and so on. We'll need to replace the fuel hydraulic actuation of the control system and look at other means of supplying that. And we'll need to update the control system. As soon as we sort of add complexity to the way we manage the various valves, actuators, and control devices, we'll then need to be able to integrate them into a new fuel system control. We're choosing to, sorry, could you go back? Yes, sorry, thanks. We're choosing to find ways of making the system safe. So we will also need to explore ways of supplying, purging, and venting the hydrogen. And we'll also need, in aerospace, we will need to have very good control of our part lives and the expected stress capability, or the functional capability of the components. We tend to, for weight reasons and installation reasons, we have to design to reserve factors of only just above 1, safety factors, and so we have very, very good control of our lives as part of this quest for high power density. So making sure we fully understand the risks around that is very important. What we're trying to do in the program is integrate a new fuel system architecture, and with a baseline engine that has its own complexities. We've got to, the target is to provide credible hardware that people can conceive can be optimized to fit in an aircraft, and we need to integrate a new test site and stand. And what I wanted also to draw your attention to is that there are lots of organizations with rules and regulations on how to apply hydrogen, but when you ask the question of how we're going to do it in the gas turbine, civil aviation gas turbine environment, there is no one document. So one of the activities we've been pulling together is trying to amalgamate the requirements from these organizations into one place, look where they got duplications, and then by trying to do this, try and develop recommendations on the way regulations could be shaped in the future. And as you may have noticed on the previous slide, feed into some of the programs of regulatory alignment around hydrogen. Next slide, please. So I draw this to your attention. I wanted just to sort of reflect on the way, the reasons for paying attention quite significantly to regulation, and also in this program to trying to take a rigorous approach to our hazard assessment. What I'm going to show here is a sort of bow tie approach. If you look in the reference in the corner, that's a Civil Aviation Authority website, which sort of describes the process here. But we've purposely taken a rigorous approach to documenting how we're addressing the various hazards we see as we move forward, because we think that learning will be value to a product in terms of determining regulations that we want to follow, but also documenting and recording our approach to the various risks and issues around putting hydrogen into passenger applications. So you can see there in the centre, the event we're looking at is gaseous hydrogen release. That's unintended gaseous hydrogen release for us would be a bad thing. Aerospace relies on lots of things working very closely together, high in the air, and having any of them do bad things is not good. And so we need to manage those risks rigorously and show that they're mitigated. And you can see on the right the kind of outcome of gaseous hydrogen release is shown in the column in red. And in the if you like, the rectangles between that outcome and those red because the event and those outcomes are the various ways of mitigating hydrogen release. So you can see we've got there ventilation, purge and fire suppression, and looking at materials compatibility. The column on the blue column on the left is the kind of things which could cause hydrogen release, and you can see that our mitigating actions there are things like design, condition monitoring, and instructing the test crew appropriately. And we're looking to document how we believe we can come to an acceptably safe outcome for various events. And you can see there we've got various safety strategies using a safety onion approach. For us, obviously, the one in the middle, the sort of salmon pit, the pink, prevention is the best means of mitigating a particular event. So design is a prevention, as is ventilation, and then various other things like controlling the environment and ultimately managing the hazardous event, a progressively less optimal means of controlling hazard. So the reason for saying this is one thing we've taken on this project is trying to be extremely rigorous in the way we approach the safety case for what we're doing. And as that, we're learning stuff and the kind of question set we need to address as we move forward into the vision of applying hydrogen to aerospace. Next slide, please. So this chart really is sort of showing where we're at and the kind of questions we're left with and are wrestling with. We're trying a design to avoid the unintended release of hydrogen. It has its own problems, which we're currently wrestling with. We're trying to make sure the system purges and vents correctly to avoid the accumulation of hydrogen and avoiding ignition sources. And we're separating hazards appropriately so we don't get any common cause failures. Currently, our test article is intended to be significantly sales remote from humans while we operate it. That's not a sustainable position. We need to be able to operate, hydrogen products in proximity to humans, but we're not there yet, and we're working out what questions we need to answer before we get there. We need to agree appropriate working practices and shutdown procedures and fire detection and mitigation, and how they apply to aerospace activities. And we'll be operating this engine on the best kind of weather, and we need to, the inverse of these questions are the kind of things we need to look at before we move to production. So there you can see this moves towards the kind of challenges for aerospace use of gas turbines. We need robust design processes. I think there's an argument for improving the way we connect hydrogen fuel systems and making sure they're as compact and tolerant to aerospace environments as possible. I think we need to think about system start and shutdown procedures, and that needs to be compatible with the use cases. So if you think that we want to ultimately apply these to EasyJet products, you can imagine the turnaround time of less than half an hour at airports is a real challenge if there are any startup or control issues with starting in the gas turbine that quickly. We need to agree standards around separations, ignition prevention, what the impact of long-term exposure to low levels of hydrogen is, and so on, fuel supply impurities, and so that the industry can agree those, and we can agree an acceptably safe stand on those issues. So that's why we're taking the rigorous approach. You can see the exciting times we're having pulling together the hardware for the engine test later this year, but we're also trying to add precision to the questions we need to answer in order to move that hardware on towards an actual product application. So with that, I think I'm on my last slide. In my next one, I think it's the last slide. So fundamentally, the conclusion is hydrogen could play an important role in future decarbonisation of aerospace, but there are a lot of challenges, technical and commercial, in maturing the technology. We're committed to developing technical solutions. That's why I'm here. It's also why I'm telling you about it, so we can share the progress and some of the challenges that remain. And we learn from collaborative hydrogen technology programs. Hopefully I've been able to see that, and we're hopefully improving the state of the art. We've got a structured and practical full-scale test program ongoing now, and we've got the underlying component to material technology programs to support that. So with that, that is my presentation, but I'm very happy to take questions. I appreciate it.
Thank you. Thank you very much. We will for sure have some questions from on-site participants. They are shy, a little bit, or tired. Rui.
Okay, congrats about your presentation. You show in one of your slides like the electrifying the aviation, especially small aeroplanes, with batteries. Or what do you refer in batteries, hydrogen, fuel cells? What do you think the batteries, they have space enough or weight enough to be part of the aviation field?
So we've studied this for several years now. We keep a watch out on that. I think the considered view on our point is contained in that file, is that it works in certain sizes of application, aircraft application. We think some of the challenges of long range, so for example 787 or A350 long range travel, are such that the fuel efficient, the fuel burn efficiency outweighs the sort of advantages of electrical propulsion. So, and in our view, the kerosene powered aircraft will be with us for a long time, because fundamentally kerosene is an incredibly energy dense way of storing energy that can be turned into power. So it'll be a long time before electrical systems are dense enough, with the power dense enough to compete with that.
Thank you. I have one from the online audience. Thank you very much for your excellent presentation. What is the typical range of distance that an aircraft powered by a hydrogen combustion gas turbine can cover during a flight? I'm
not going to be very precise on this, because I'm not an aircraft designer. We contribute to that debate. What I would say is the market we're targeting is the kind of EasyJet market, the A320. So you can imagine those aircraft may well be 700 nautical miles, maybe 1,000. They have a maximum range of a couple of thousand nautical miles, but the sort of typical range is the airplane you might take to visit me in Derby if you came from Porto. That sort of plane.
Question, André?
Duncan, good afternoon. Thank you for the presentation. Somewhere I've read that the European Commission was thinking about wiping out of the program flights underneath 500 kilometers of distance, if I'm not wrong. Somewhere I have read this. Does this still maintain? This means that aviation under 500 kilometers of distance will be substituted by, I don't know, train traffic? And the second question is between the special characteristics of security involving hydrogen towards, for example, and for instance, methanol. Have you already developed and tested the methanol alternative in Rolls-Royce turbines? Thank you.
Nice. Let me answer the first question first. But I'm sorry, I will provide a view on the first question. So Rolls-Royce, and my job in Rolls-Royce and Rolls-Royce's view in particular is that we mature technologies ready for a market application, and some of those decisions about trains versus planes will be agreed by society. It's a society-driven thing. Regulation might influence it, or the rate of development of other technologies will influence that strongly. So Rolls-Royce remains capable of interacting in both markets. We supply power systems to trains as well. I'm sort of focusing on the options that we're trying to develop here. Your second question, so the other job we have in Rolls-Royce is to horizon scan. So I can assure you that we look at other fuels. Hydrogen's probably we picked that because it's most likely to be carbon neutral, carbon zero carbon, but it's also possibly the most difficult fuel. I would draw your attention, of course, to the low melting point and the difficulty of storage and the leakiness and the combustibility. So while that has some advantages, it's a real challenge which we're learning about. And that's as an engineer, I'm actually worried about the detail challenges. How easy it is to make two units join together and transmit hydrogen, but how can you make that such that someone can fix that joint late at night in 5 minutes while the plane's waiting on the airport, and they can do it safely, and that joint then won't leak. So it's that moving on from science to practical applications I'm really concerned in. So we do look at various fuels. I think what we're trying to do is learn from hydrogen, and certainly a lot of the lessons we're learning will be applied to methanol or other gases, gas kind of fuels.
Okay, thanks. I have another from the online audience. Great presentation on great work. My question is, considering the high costs of hydrogen as compared to conventional fossil fuels-based energy, since the companies are only driven by financial considerations, will they consider it a viable choice, and why?
Yeah. I mean, really, multi-billion, $100 billion question there. I'm not going to say I know the answer to it. What I would observe is that we found it hard to source green hydrogen because I suspect the infrastructure is not there, and we're only trying to test. Our engine there will do 20 or 30 hours of running. We're not able to find the green hydrogen necessary to support that. So, yes, I think it's going to be a massive problem. I think it will dominate the decisions. I think, however, if society chooses to commit to green work, I think we stand ready with the technology. But then once you've decided that, there's then quite a lot of things to solve before you get to a product. What I'd also note is, I'm sure you're aware, is that there are other easier targets for the use of hydrogen than aviation. So I wouldn't expect aviation to be some of the first applications, first users of the green hydrogen.
Okay, thank you. The very last question over there.
Thank you for the presentation. It was really interesting and a good learning progress for us. I had a question. When you're retrofitting the current existing turbines to work on hydrogen, does it affect the weight of the turbine? And if it does, is it something that would also affect the economics behind the operability of the aircraft? What is your take on that?
I think it's a really interesting question. That is something we think about. So I'll perhaps divide it into two, if I may. I think the weight is a question of component efficiencies, component structural behavior, and so on. And I think what we're thinking is that the fuel, in a sense, won't really impact that, provided we're creating the right heat in the combustor, that the rest of the system sort of follows that. So I don't expect it to change the weight of what we produce. There are some details in that. Clearly we need to make sure hydrogen is compatible with the components we use in those, and that may change that position. I think the sort of second question on economics is perhaps more of a system or a platform, an aircraft level decision. If the means of storing that hydrogen that you need to achieve a given mission are less energy dense than equivalent kerosene storage systems, then you will impact the aircraft design, you'll impact the range capability, and thus the economics. So there's a complex interaction financial model that would be impacted by possibly the aircraft changes rather than the gas turbine changes. If that makes sense.
Yeah. Thank you very much.
Okay, and with that we end. Again, a warm applause to our speaker today.
Thank you very much for having me.
Thank you very much, Duncan. Great.
Goodbye.
Bye-bye. And then we have our second coffee break of the day. Okay, hello again. We will have now the last presentation of today. I will present my colleague, but before that, I want to inform you that at 7 o'clock we have a bus driving all of us to WOW, the WOW place, the WOW place, which is where we will have our dinner. So 7, the bus, and it is in the entrance of the faculty, near the flags. In fact, we don't have flags, but the site of the flags. So, I am very pleased to welcome my, again, colleague and friend, Rui Neto, from the EST. He's a mechanical engineer.
And chemical.
And chemical, you are both. So he will present us quite interesting presentation on the economic value of implementing hydrogen stations in Portugal. So you have the floor, Rui.
Okay.
30 minutes, because we still have a visit to our lab.
Okay, thank you very much, Alexandra, for your very well-organized summer school. Thank you very much. It's always a pleasure to be here, to come to Oporto, to this great team, and also thank you very much for the public to handle and to resist until the end of these very hard top sessions on hydrogen and fuel cells. Okay, thank you very much. My presentation, I promise that I'm going to be brief. I'm going to talk about the refueling stations, hydrogen refueling stations. Okay, so as you can see here, it's the importance of the hydrogen refueling stations. We are made of, in weight, of 10% of hydrogen, because we are made of water and also polymers and so on, biomass, and 10% of our weight is hydrogen. But if we count the number of atoms of our body, we are made of 75% of hydrogen atoms. So hydrogen is a raw material that is everywhere, and we can find it everywhere, okay? So that's why we can pick up even hydrogen in the atmosphere, that even in the desert we have water in the air, we can condense it, and we have raw material to produce hydrogen everywhere in our backyard even, okay? So, why hydrogen is now, the global hydrogen momentum is now, okay? What are the main pillars of the decarbonization? Security, industrial applications, and also energy security. We need to have energy security, because if you remind, in Europe, especially in Portugal, we don't have hydrocarbons. We don't have natural gas. We have to import everything from other countries, like from Iran and from Middle East or from USA. So we depend a lot in the way we import energy. So that's why it's a big importance to change vector or raw material. Hydrogen is also a raw material to produce other products that we need and we consume in a daily basis. So, as we can see here, Portugal energy landscape, what are the challenges, you know? We dependent on fossil fuels, and we developed the economy of fossil fuels during 130 years, okay? These images, as you can see, are art from AI, okay? I did it, because they are very difficult to produce, and AI produced me the image for me, okay? So Portugal, it's a very right place to do this. Why? Because we have lots of solar energy. So we are, and solar energy is very abundant and infinite, okay? It's not, so we can use this energy to convert using electrolysis to produce hydrogen, to do whatever we want, including to package energy to our transportation, okay? So what are the challenges? So hydrogen is not really found in the nature in the hydrogen gas, so we need to convert from water or from biomass, as we already know it. And why Portugal? Because we have abundant, we are a peaceful country, We have already lots of infrastructures prepared from natural gas, and we can replace this natural gas in some component to hydrogen. So we have the refilling, we have the tank to storage natural gas, so we could add also some hydrogen there, and we don't need to pay another tank to storage hydrogen. So hydrogen, we can use it especially in the sectors that are very hard to abate, okay, like glass industry, cement industry. After the water, the cement, I think, is one of the main raw materials that we consume in all the developed societies, okay? So we need to make buildings and structures, bridges and infrastructures, so we need to produce cement, okay? So use hydrogen in the cement industry to improve the efficiency, and is also a great goal. Hydrogen and oxygen, okay? So here, I have also here another application that hydrogen can be very differentiated. It's in train stations. But as you can see here, if we compare the hydrogen trains, diesel trains, and electrical trains with catenary, so if we have already like catenary, it doesn't make sense to use hydrogen there. But as you can see here, the main, in Germany, UK, India, only a small fraction of the lines, they are electrified. So you can use hydrogen there. And the cost of electrifying a line in Germany is around 1 million per kilometer, okay? In China, it's much lower. In Portugal, about 3 million per kilometer. So to put electrifying in the trains, it costs a lot. So it's maybe more cost competitive to put a fuel cell in the train, and we can use also this train in some regional lines with not so intense utilization, okay? So this is everything that is heavy like a train can be used and converted to hydrogen. So regarding to refueling stations, as you can see here in this slide, we have this map, and this map is always updated. We have refueling stations almost everywhere. The greens, they are opening. The grays, they are already old projects, and the yellows, they are in construction, okay? As we can see here in Portugal. In China, we have already 400 refueling stations. Japan, around 170. UK and Germany and other 100 stations. In Portugal, we have around between 2 to 4 stations. Some of them, they have some difficulties to opening just because regulation and some bureaucratical problems, you know. They need somebody to sign that says that it can open to the public, you know. But right now we have around 1,200 stations, and especially China has around 1/3 of these stations in the world, okay? So here we have, what makes a refueling station, what are the main components of a refueling station? We have several possibilities. We can put the electrolyzer there, okay? We need a compressor to compress the hydrogen to 700, 900 bars. So we could fast refilling the fuel cell or internal combustion engine vehicles, okay? So we have the dispenser. All these components, they have a certain cost and a certain complexity. So we need also to adapt these components to, if we ask to some Portuguese authorities, they certify this, supervising this final opening to the public. They say, oh, this is like a chemical industry, so they look to a single refueling station as a very complex refueling station. So this creates some problems in terms of massification of the refueling stations, okay? We can produce hydrogen using 7 possibilities. We can produce on site, or you can produce in the decentralized way, okay? We can produce electrolysis, we can have a local electrolyzer, or a steam methane reforming. We can also have like a steam methane reforming locally to produce, and we can also do the capture of the CO2 locally or centralized, okay? There are different pros and cons regarding to this approach, but I believe like the refueling stations that will dominate in the future will be more decentralized because they make sense. We have local electricity and we have water, so we can do everything locally without the decentralized makes sense in terms of the scale economy of the oil, you know. We should think in a different way instead of oil. So this is the centralized, as you can see here. We have like the production, delivering, compressed, distribution, and refill. Here, it's more the concept of the decentralized hydrogen refueling stations. As you can see here, the dispenser, we can refill the vehicles using compressed hydrogen or liquid hydrogen. There are always some heavy industry, like every truck industries, they can use liquid hydrogen to have to storage more energy. But I believe that the dominant solutions in refueling stations will be the compressed. The cost of hydrogen, it depends a lot on the cost of electricity. And if we have a very expensive electricity, it means that hydrogen will become also very expensive, okay? So even if we have the electricity very cheap at zero during the midday, but we still have to pay the infrastructure, the grid infrastructure, because the grid is there, the transformation, so we need to cost all of this infrastructure. So the final cost of hydrogen, mainly it depends a lot on the final cost of all the infrastructure, okay? So here, the electrolyzers, as we already saw it in the morning, it can be different technologies. We have the PEM, the alkaline, solid oxide, and even the capillary electrolyzers, okay? The capillary electrolyzers, they promise a very high efficiency, okay? If the electrolyzer has the efficiency of 90%, we just need to cool down the electrolyzer 10%, remove 10% of the heat, okay? And this will simplify a lot the CapEx and OpEx of the operation of the electrolyzer. So, but these types of technologies, they depend a lot also in terms of safety regulations, advanced compressed solutions, and so on. Regarding to the infrastructure requirements, as I told you previously, we need to considering lots of players, like space considerations, utility connections, electricity, water. We should guarantee all of these layers are compatible, okay? And all the different players, they need to sign the documents, they do this in the right time. Just, I know some real projects that if, like the municipality, they don't have experts inside to know these types of standards and regulations. So they need to hire some academics to say if this, what are the best, because they don't have enough expertise, they don't have enough engineers to understand what they are approving, you know. So there are lots of constraints regarding to the permitting and the regulation compliance in the different value chain if you want to implement a refueling station in your backyard, okay? So that's why this brings some challenges that we need to, as academics and as an industry, we need always to fight just to help to implement our refueling stations. Regarding to the value to the economy, if you install refueling stations, this can create lots of direct jobs. You need to build the refueling stations. You had very high value locally jobs. You need to build the infrastructure. And also you create indirect jobs, okay? And you create new problems, new challenges that can help to stimulate this economic development, okay? In Portugal, what we can see here, refueling stations economy are more close to the oil economy, because if you have, you can refill your car in 5 minutes, you know, it's like the oil, okay? Lots of persons can go to refueling station to refill, you pay like a percentage of your refilling and you can cost easily this refueling station. If you have like a battery car, you just depend on yourself. If you have a garage or parking, you can refill your car in your garage or parking, but it's only a single person to cost this recharge infrastructure. In the hydrogen, it's more close to the economy of the fossil fuels, okay? So, we can get here lots of beneficial and economical indirect value from different players. So with hydrogen refueling stations, we create more economy, okay? With battery electrification, we create, maybe reinforce the grid, create other type of jobs, but here we involve more players and we create more opportunities, okay? So, as you can see here, to electrify or to make the transportation cleaner, we have three pathways, especially three pathways. We have batteries, we can electrify batteries, and from the renewables to the wheel, this is the more efficient pathway, as you can see, okay? With hydrogen, we lose more energy in the way to the wheel to move the car. The liquid, we can also create synthetic fuels, we can pick up oil, and we lose more energy into the wheel. So, if we look to this image, it looks like the batteries are the best, right? What do you think? Why? Efficiency is everything, right? But how much is the efficiency of the photosynthesis? Do you know? How much energy can a plant capture? Yeah? 1%, yes. But the photosynthesis is a very old process, right? The nature invented and selected from natural selection. But the plant only uses 1% of the energy to produce the biomass, okay? So the efficiency is important. We should search for more efficient process, but the efficiency is not everything. And the majority of the process that we know in our daily basis, they have very low efficiency. They have been chosen not because they are very high efficient, but because they are very replicated, okay? So this is true, the first line is true, only if the temperature is 20 degrees, if the batteries of the car are new, and if they have only a few cycles. If the batteries are old, lots of cycles, the temperature are extreme, very hot or very cold, this efficiency, this is not true. It's much lower, you know? So the liquids and hydrogen, they are very adapted for fast refueling and for any type of climates, you know? In the desert, in snow, you can do it wherever you want. The batteries, they are very efficient if the right conditions are united, okay? If we look to the same, another image showing the different perspective, the energy packaging per kilogram and per liter. All of these amounts, they represent the same amount of energy. As you can see here, the liquid is here already 130 years because it's very energy compact and dense. We put lots of energy per volume and per mass in the very small space, okay? It's not the best efficient solution, but we can compact very well the energy. The hydrogen, it's very light, but with the tank, it's a little bit more heavy. And the volume, if we compare the diesel with hydrogen, it shows why the planes, they must have the 3-4 times more volume to package energy during the flights, okay? And regarding to lithium-ion batteries, do you think it's possible to put lithium-ion batteries in planes? Because the planes will be very heavy and very voluminous, okay? That's why the planes, they are very low autonomy with batteries. We can put in some drones and they work, but they don't work. This is a physical limitations, you know? That's why in all the ecosystem, there are some applications like this. Some, they will prefer the batteries because the batteries is the most adequate energy solution to storage energy. For long distance and heavy vehicles, very like big planes, big ships, and big long distance vehicles, probably the liquid will be the best. And in the middle, we have the hydrogen that it's between the electrical and the fossil, okay? So, as you can see here, and you ask me, and how much will cost to produce a synthetic fuel, liquid synthetic fuel? As you can see here, this is in 2025, 1 liter of synthetic fuel costs around 1.6 euros. And in 2050 will cost probably 0.7, okay? So right now, the synthetical fuel, it costs 3 or 4 times more than the fossil fuel that we get from the well in Saudi Arabia. Okay, that's why we are going to use like hydrogen, liquid synthetic fuel as an additive, just to help to pay the transition. Okay, because it's very cheap to go to the well to pick up the fossil fuel to do the job. Here, this is also another constraint. If we compare electrification of hydrogen and liquid and lithium-ion batteries, for example, in the old city, who lives in the old city, only a small fraction of the people, they have a car or a garage to parking the car, okay? So to recharge the batteries in a garage or parking is just for a small number of percentage people that lives in the cities, you know. With the hydrogen, you can refill hydrogen everywhere, but you don't have refilling stations. We have planned to build 100 refilling stations until the end of 2030, and we still are in the 2 or 3 refilling stations, okay? So we will not buy the cars because we don't have refilling stations. So this image here, it's a result of a student, Catarina. She did a very good work on, this is the density of Portuguese population. Majority of the people, they live in around the big cities, okay, as you can see here. So she picked up this data, and she also realized where are the fast electrical chargings. So he also considering where are the future fast electrical charging plants. And here at this slide, there are the 3,200 fossil fuel refilling stations, okay, that we implement during 130 years. So she picked up these results, this data, and we start to answer to the question, what are the best sites to place the hydrogen refilling stations to be more cost competitive? Where is the market somehow? This was the main question that you want to answer. As you can see here, we choose to put the first 30 refilling stations where the people they live, where are also the very high dense fossil fuels. And then the next 40 stations we put in the main dense regions, where are the potential market, and the last 40 stations we put in the rest of the country, okay? Just but we need also to realize that each refilling station will cost like between 5 and 6 million, okay? Just to produce 500 kilos per day, okay? So this will take time to reach to this situation here that we have 3,200 fossil fuel refilling stations. So just to highlight where we need also to help to modify the industrial sector, to help this transformation. So what are the main processes that we can combine with hydrogen refilling stations? We should have a look and look this as a great opportunities and for the new industrial and the process, and also think in terms of export raw materials like methanol. We can put methanol in chips and also to package the hydrogen in the methanol shape, okay? So like cement, steel industries, to green steel, and also fertilizers. These are the best applications for hydrogen that we can combine with hydrogen refilling stations in the transportation. As you can see here, decarbonizing the sector, we have here this image generated by AI, okay? So I just asked that AI will create me an image just focus on heavy-duty transport trucks, buses, trains, and maritime. So what he gave me was just these types of ships. Really, I don't know if this is going to be possible because maybe the hydrogen will be like methanol shape to move big container ships, you know. But this was just the interpretation, just to create a possibility as a green fuel. And also maybe we should put HVO, maybe to the planes like SAF, okay? as an indirect way of refilling vehicles. So, just to concluding, I just want to highlight we are right now in the transition stage that the economic and environmental beneficials can bring lots of opportunities to Portugal and to other countries that they believe that don't have fossil fuels, and we have the right context and the right opportunities just to develop this economy and also to create value and to create great opportunities, you know. We are in a great position just to lead this green hydrogen economy. I don't know if you have questions. Me and my team, we have lots of papers published, more scientific papers on this field, just showing that it's possible just to create refilling stations, create electrolysis projects, and make money and to create new opportunities and help to this energy transition. Okay? Thank you very much for your attention.
So, questions from the online? We don't have. Perhaps they are tired. Diogo?
Thank you for the presentation. We won't reach the number of refilling stations that we established, but what do you think, how many we will have in the next 5, 10, 15 years?
According to my data and according to see what happens with the first one, I have a student, master student, doing the master thesis in the first one. They are already finishing, and they are going to be prepared to be open to the public in August. But the difficult, I believe this refilling station can open the possibilities and to make it fast the process to the new ones, because the certification and the authorizations that you need to open, they are very, very hard, and especially from the JEG and from the other HAPA, just to show that it's just a new refilling station, a way of, so I believe the next, until 2030, maybe we can not install 100, but maybe if we install 30 or 40, maybe it can be already like a good target.
Let's hope so. Thank you.
Questions? More questions? You want to go to dinner? Okay. The one you are talking is where?
Is in Cascais, Cascais Próxima. Is Cascais Próxima. Cascais, they already have like 4 Caetano bus hydrogen buses. They already ordered more 6, and they have the ambition to have 14 hydrogen buses just to
I think we will have here in the north also.
Yes, like, because you have the factory of the buses, yes, right? In Vila Nova de Gaia and Ovar. So, but if you don't have refilling stations, you cannot buy so that's why it's important. And by the way, this refilling station cost around between 5 to 6 million, and it was just supported by the municipality budget. They didn't enter in the special program because they still believe that this is the way. Okay, and they did the calculations. They are going also to install like a PV. Local production electricity, so they don't need to buy so much electricity from the grid.
Okay, Misha, thank you.
Yeah, I also had a question about the distribution of the distribution analysis for the refueling stations. I guess in the beginning they will be targeting things like buses, so it also makes sense to have them in cities. But if you go one step further, when it's more about maybe trucks, then maybe you would actually not necessarily want to have them in your population centers, but along the highways where the largest volumes of traffic go for long-distance transport. But I didn't see that from, let's say, the initial analysis, because there were some gaps.
Yes, this is just a more generalistic presentation. You know, we have papers also on that, and we are preparing some papers on that. But this refilling station is also prepared, so you could pick there like a trailer refill this trailer and distribute in the surroundings, you know. So they just plan this refilling station that can be like a hub to distribute to others. Okay?
All right.
Because this will take time, but because it will take time, this is very important to be operating because this will show the way to the others, you know. The first ones are always the more difficult ones, you know. While this is done, I believe the others will come faster.
Okay, thank you. It is like the first electrolyzer by Cummins in Canada, and
Yeah.
they learned a lot with
Yeah.
the operation. So, I think we are done. So, don't forget to join us in the bus and at dinner. Of course, you can go directly to WOW. Also, we have the visit to the labs, and for those who are going to the visit, please gather at the check-in desk, okay? So thank you very much. Welcome.
Thank you.